You've been told the moon has a dark side. That's a lie. Every part of the moon gets sunlight. The far side of the moon isn't dark. It's hidden. And what NASA found there is far more terrifying than any shadow. Because it's not about monsters or aliens. It's about a silence so deep it could unravel everything we know about our place in the universe. You've never seen this place. No human eye ever has, not one. For all of history, our species has looked up at the moon, watched it wax and wane, told stories about the man in its face, used its light to navigate oceans. But half of it was always turned away. Not because it's shy, not because it's dark, but because the moon is locked in a gravitational embrace with Earth. It rotates exactly once per orbit. That means one hemisphere always faces us, the other always faces away. That's tidal locking. It's not magic, it's physics. But that hidden half, the far side, has haunted us. Ancient cultures filled it with gods and demons. Modern conspiracy theorists filled it with alien bases. And for decades, we had no way to check. No telescope could see past the limb. No photograph existed until 1959. That's when a Soviet probe named Luna 3 swung around and sent back grainy, ghostly images. And what they showed shocked everyone. The far side wasn't a mirror of the near side. It was completely different. The near side we know is smooth in places. Dark plains called Maria, ancient lava flows, cover about a third of it. They form the familiar patterns we call the man in the moon. The far side has almost none of that. It's rugged. It's piled high with craters upon craters, mountains sharper than any on Earth. It looks like a battlefield, and in a way it is. The largest scar on the entire moon, maybe the largest impact scar in the solar system, lies on the far side. It's called the South Pole Aitken Basin. It stretches nearly 2,500 kilometers across. That's wide enough to swallow the entire United States. Its floor sinks more than 8 kilometers deep. If that crater were on Earth, it would reshape continents. The impact that carved it was so violent, it may have punched through the moon's crust, exposing the mantle below. But here's the thing. We still don't know exactly what's down there. We have hints. Orbital instruments detected minerals that suggest deep rock was dragged up. But later lava flows may have buried the evidence. The basin is both a window and a veil. And it holds something else. Something that makes the far side terrifying in a way no alien could match: ice. In the deepest craters near the South Pole, sunlight never touches the floor. The geometry is extreme. The walls are steep. The sun hangs so low on the horizon that its rays never reach the bottom. Those craters have been in permanent shadow for billions of years. Temperatures there plunge below minus 230 degrees Celsius, colder than the surface of Pluto. In that absolute cold, any water molecule that wandered in, delivered by comet or asteroid or solar wind, would freeze instantly and stay frozen for eons. NASA's ELSROS mission proved it. In 2009, they crashed an empty rocket stage into one of those craters. The plume that rose up contained water vapor, lots of it. And not just water. Methane, ammonia, carbon dioxide, even organic compounds. The far side is a frozen pantry of cosmic chemistry. But the ice isn't just a resource, it's a time capsule. Every grain preserves a record of what was flying through the early solar system billions of years ago. If we can drill into that ice, we might read the history of water itself. And water is the key to life. That's one reason NASA and other space agencies are so focused on the moon's poles. But there's a tension here. Why does Mars get so much attention while the far side of the moon remains barely explored? The answer is simple. Mars is a planet. It has an atmosphere, seasons, and evidence of ancient rivers. It's the best candidate for past life. The moon, by comparison, is a dead rock. But that's exactly why the far side is so valuable. Its silence is an asset. Think about radio silence. On Earth, we're drowning in electromagnetic noise. Every radio station, every satellite, every Wi-Fi router, every radar pulse fills the air with signals. Even from orbit, you can't escape it. But on the far side of the moon, the bulk of the moon itself blocks all that noise. It's the only place in the inner solar system where you can truly listen to the universe without human interference. Astronomers dream of building a radio telescope there. Not a visible light telescope, a radio array spread across kilometers of dust, tuned to wavelengths that can't penetrate Earth's atmosphere. With that, we could hear the faint hiss of hydrogen from the cosmic dawn, the signal from the first stars igniting. We could listen to the birth of structure in the universe. That's not speculation, that's physics, and the only place to do it is the far side. But here's where it gets unsettling. The silence of the far side isn't just a scientific opportunity. It's a reminder of our isolation. When Apollo astronauts orbited the moon, they spent about 50 minutes on each orbit behind the moon, completely cut off from Earth. No radio, no voice, no signal. Michael Collins, alone in the command module while Armstrong and Aldrin walked on the surface, later described that solitude as profound. He said, "I am alone now, truly alone, and absolutely isolated from any known life." That was on the near side. Imagine that isolation on the far side, where Earth never rises, where you can never look up and see your home planet, where the sky is only stars. That kind of isolation isn't just psychological, it's physical. The far side is harder to reach. You can't communicate directly. Any mission there needs a relay satellite orbiting in a halo position to bounce signals around the moon's bulk. That adds complexity and cost. That's why, for decades, every single lunar landing, every surveyor, every Luna, every Apollo touched down on the near side. The far side remained untouched by human machines until 2019. That's when China's Chang'e 4 mission made history. They landed in the von Karman crater inside the South Pole Aitken Basin. They deployed a rover named U-22, Jade Rabbit. It's still crawling across that alien terrain, sending back data. Its ground-penetrating radar has revealed layers of ejecta from ancient impacts. It detected material that may be from the moon's mantle, and it survived far longer than its design life, enduring 2 weeks of scorching daylight, followed by 2 weeks of brutal night, over and over. But Chang'e 4 is just the beginning. NASA's Artemis program aims to return humans to the moon, and this time, the poles are the target. The far side is on the table. There are plans for a lunar base near the South Pole, where peaks of eternal light provide near-constant solar power and shadowed craters hold ice. A base there could serve as a refueling station for missions to Mars. It could host that radio telescope. It could become a permanent human outpost on another world. But that vision comes with questions. Should we mine the ice, consuming a record of cosmic history for fuel? Should we preserve the far side as a quiet sanctuary for science, protected by international treaty from interference? Or should we treat it as a frontier, open to competition and colonization? These aren't just technical questions, they're ethical, and they're urgent, because the technology to go there is real. The political will is building. The far side will not remain empty forever, and that's where the terror comes in. Not from aliens, not from secret bases. The terror is the silence itself. The far side is a place where Earth is invisible, where you are truly alone, where the only sounds are the hum of your own life support and the crunch of regolith under your boots. It is a mirror that reflects our own fragility. We are a species that evolved under a sky with a familiar moon. We are used to looking up and seeing that pale face. Take it away, and something fundamental shifts. Astronauts who have seen Earth from the moon describe the overview effect, a profound sense of unity and fragility. What would it feel like to live where Earth is never seen, to be permanently cut off from the sight of home? That's the real story of the far side. It's not about what's hidden there. It's about what's missing. The familiar, the anchor, the blue marble in the black. Without it, you are adrift. And yet, that drift might be exactly what we need. To stop looking back, to start looking outward. The far side is the threshold, a place where humanity can finally turn its gaze away from its cradle and toward the stars. That's terrifying, and it's also exhilarating. So, what did NASA find on the moon's dark side? They found that it isn't dark. They found the largest impact scar in the solar system. They found ice cold enough to freeze time. They found magnetic ghosts and hidden mascons, and a silence so perfect the cosmos can finally be heard. They found a place that is both barren and rich, dead and alive with potential. They found our next step, and they found a mirror, a reminder that the unknown isn't something to fear. It's something to enter, step by step, rover by rover, footprint by footprint. The far side is no longer a blank oval on a map. It's a destination, and the only thing terrifying about it is how long it took us to go there. But now that we are finally going, the questions multiply faster than the answers. Why does the far side look so different from the near side? That asymmetry isn't a small curiosity. It's the central mystery of lunar science. The near side is dominated by vast, dark plains of solidified lava, the Maria. The far side is almost entirely bright, cratered highlands. Only a handful of small Maria exist there, like Mare Moscoviense and Mare Orientale. The contrast is so stark that when the first images came back from Luna 3, scientists refused to believe them. They thought the camera had malfunctioned, but it hadn't. The leading explanation for this split personality involves crustal thickness. Measurements from NASA's Grail mission, twin spacecraft that mapped the moon's gravity in unprecedented detail, showed that the far side's crust is on average about 60 kilometers thick, roughly double the near side's 30 kilometers. That extra thickness acts like a lid. Magma couldn't punch through to flood the surface. On the near side, the crust was thinner, so lava erupted easily, filling impact basins and creating the smooth, dark plains we see. But why is the far side's crust thicker? That's where the debate gets heated. One hypothesis points to the moon's formation. The giant impact that created the moon left it molten, a magma ocean. As it cooled, lighter minerals like plagioclase floated upward to form the crust. If the cooling was uneven, perhaps because Earth's heat slowed solidification on the near side, then more crust could have accumulated on the far side. Another idea is more dramatic. The moon may once have had a smaller companion, a second moon, perhaps a few hundred kilometers across, orbiting Earth alongside the main moon. Over time, tidal forces pulled them together, and the smaller one collided, not violently, but gently, almost like a merger. Its debris splattered across one hemisphere, thickening the crust. That theory is called the giant impact double whammy, and it's speculative, but it fits some of the data. Then there's the possibility that the South Pole Aitken impact itself was so colossal it redistributed mass, causing the far side crust to thicken as a kind of rebound effect. Each idea has its champions. None is proven. The far side keeps its secret. But the differences go deeper than just crust thickness. Radioactive elements like thorium and uranium are concentrated on the near side in a region called the Procellarum Creep terrain. That name comes from the chemical signature, potassium, K, rare earth elements, Re, and phosphorus, P, indicating the last dregs of the magma ocean. This concentration of heat-producing elements kept the near side's interior warmer longer, promoting volcanic activity. The far side, deprived of that internal furnace, cooled into the rugged cratered highlands we see. So the moon's two faces are not just different in appearance, they have fundamentally different thermal histories. They are two worlds frozen in a single sphere. And that's where the terror creeps in again. Because if the far side is a dead, cold, silent world, it's also a pristine archive. Every crater on the far side is a fossil, untouched by lava flows that resurfaced the near side. The earliest history of the solar system, the late heavy bombardment, when comets and asteroids rained down on all the inner planets, is written more clearly on the far side than anywhere else. Scientists estimate that impact craters on the near side have been buried or erased by volcanic resurfacing. On the far side, they remain, layer upon layer, like pages of a book. But here's the chilling part. We can't read that book fully yet. We've only seen it from orbit. We've sampled a few rocks from the near side. We have none from the far side, except for one possible exception, a lunar meteorite found in Antarctica called Northwest Africa 4824, which some scientists believe originated from the far side. But that's just a fragment, a whisper. The full story lies buried in those endless highlands. Right now, the most ambitious plan to get answers is China's Chang'e 6 mission, scheduled for launch in the mid-2020s. It aims to collect samples from the South Pole Aitken Basin and return them to Earth. If successful, those samples could settle the debate about whether the basin exposed mantle material. They could date the impact event precisely. They could reveal the chemistry of the far side crust, and they would be the first samples from the far side ever brought back. That's a big deal, but it's also a reminder of how much we don't know. For decades, the far side was a blank space on maps. Now, it's a blank space in our sample collections, and every gram of rock we bring back will rewrite textbooks. But the terror isn't just about what we don't know. It's about what we do know and what it implies. Take the moon's seismic activity. The Apollo seismometers operated from 1969 to 1977, recording thousands of moonquakes. Most were deep, triggered by tidal forces from Earth. But some were shallow, and they were violent. One shallow moonquake in the 1970s registered about 5.5 on the Richter scale, enough to rattle a building. If that had happened near a future base, it could be catastrophic. And here's the disturbing part. All those seismometers were on the near side, We have no idea what kind of quakes shake the far side. The crust is thicker, so quakes might be less frequent, or they might be more intense because stresses build up differently. The only way to know is to put seismometers there. That hasn't happened yet. So when we talk about building a base on the far side, we're planning to construct a home on ground we have never felt tremble. And the tremors aren't the only hidden dangers. The moon's magnetic field is a ghost. Today, it's weak and patchy. But in the past, it was strong enough to magnetize rocks. The Apollo samples revealed that some rocks had been magnetized in a field as strong as Earth's. That suggests a lunar dynamo, a liquid iron core churning like our own, once existed. But how? The moon is too small. It should have cooled and frozen solid long ago, yet the magnetic evidence persists. Some scientists think the dynamo was kick-started by the constant tug of Earth's gravity, flexing the moon's interior and stirring its core. Others think it was powered by the crystallization of the core, releasing heat. Either way, it stopped. And when it stopped, the moon's surface became exposed to the full force of the solar wind and cosmic radiation. That radiation has been bombarding the far side for billions of years, altering the chemistry of the regolith, creating a layer of space weathering that changes how the surface reflects light. The far side, with its thicker crust, may have a different radiation history. That matters for any long-term human presence. You can't just build a base. You need to bury it under meters of regolith to shield against radiation. That's engineering. But it's also a reminder. The far side is not a gentle place. It's hostile in ways we are only beginning to understand. And then there are the swirls. On the far side, near the antipode of the South Pole Aitken Basin, there are strange, bright swirls in the soil. They look like wisps of smoke frozen in place. They are called Reiner Gamma-type swirls, and they are associated with local magnetic anomalies. The magnetic field is weak, but just strong enough to deflect solar wind particles, protecting the surface from darkening. So, the swirls are actually patches of relatively unweathered, bright soil. They are like magnetic shadows, preserving the original color of the lunar surface. But why are they there? The leading theory is that the impact that created the South Pole Aitken Basin sent shockwaves through the moon, and those shockwaves compressed and magnetized rocks at the exact opposite point. That's right. A cataclysm on one side of the moon left a permanent magnetic fingerprint on the other. It's a connection across thousands of kilometers of solid rock. That's not just geology, it's almost poetic. Violence and its echo. The swirls are also a resource. If those magnetic anomalies can shield solar wind, they might also offer some protection to future explorers. But they're tiny, only a few kilometers across. You can't build a city on a swirl. Still, they hint at a deeper truth. The moon's interior is not homogeneous. There are density variations, magnetic variations, and composition variations that we have only begun to map. The Grail mission gave us a gravity map with resolution down to a few kilometers. It revealed that the far side has its own mascons, mass concentrations, buried beneath some basins. The most famous is in the Mare Moscoviense, a small lava plain on the far side. That mascon is weaker than those on the near side, but it's there. It tugs at orbiting spacecraft, subtly altering their paths, and those tiny perturbations can be measured to infer the structure below. It's a kind of gravitational archaeology. But for all our orbital reconnaissance, the far side remains a place of absence. No human has stood there. No rover has drilled deep. No seismometer has listened to its heart. The silence is not just radio, it's scientific. And that silence is what makes the far side both terrifying and alluring. It's the last blank spot on the map of human experience within our reach. Mars is farther. Venus is hotter. The gas giants are impossibly distant, but the far side is right there, just 400,000 kilometers away, and we haven't set foot on it. That's not a failure, it's an invitation. So, what will we find when we finally go? The ice? Certainly. That we know. But what about the deeper secrets? The South Pole Aitken Basin might hold fragments of the moon's mantle, giving us a direct sample of its interior. That could test theories of the moon's origin, and by extension, Earth's origin. The polar shadows might contain not just water ice, but also frozen carbon dioxide, methane, and ammonia. Those are the building blocks of life. If they are present in significant quantities, they could be used to make rocket fuel, breathable air, even plastics. The far side could become a supply depot for the entire inner solar system. But the most profound discovery might not be physical at all. It might be the change in perspective that comes from living there. Every culture on Earth has grown up under the same moon. Its familiar face has been a canvas for stories, a clock for seasons, a steady companion. To be on the far side is to be cut off from that, to look up and see a sky where Earth never appears. That is a psychological shift unlike any other in human history. It's not just the overview effect, it's the hiddenness effect. You are in a place that has never been seen by any ancestor. You are truly, utterly alone, in a way that even deep space astronauts have never experienced. And yet, you are not lost. You are on a world you have come to inhabit. That is terrifying, but it's also the next step in our species' maturation. We left Africa and populated every continent. We crossed oceans and built civilizations on islands. We reached the South Pole and the deepest ocean trenches. Now we stand on the threshold of a new kind of isolation, one that forces us to rely on ourselves, our technology, and our ingenuity. The far side is not a place of alien monsters. It's a place that will show us who we really are. And that's what NASA found. Not evidence of another intelligence, but a mirror. In the silence, in the ice, in the craters, in the magnetic ghosts, we see our own reflection. A species that has the audacity to look beyond its cradle. A species that can survive in the harshest environments. A species that can listen to the universe's faintest whispers. The far side is not a dead end. It's a beginning. So when you hear someone call it the dark side, correct them. It's not dark, it's hidden. And the only thing hiding there is the future. A future that is already arriving, one rover, one orbit, one sample at a time. The far side is no longer a mystery. It's a destination. And the journey has only just begun. That journey will require us to solve problems we've never faced before. How do you land a spacecraft without direct communication? The answer is autonomous navigation, letting the computer guide itself using pre-mapped terrain. NASA's autonomous landing hazard avoidance technology has already been tested. How do you keep a base powered through 2 weeks of night? Nuclear fission reactors, not solar panels. NASA is working on the Kilopower project, a small, reliable nuclear reactor that could provide tens of kilowatts continuously. How do you protect against radiation? Bury the habitats under meters of regolith, or use inflatable structures that pack rigid shielding into their walls. Each of these technologies is being developed right now. The far side is not a pipe dream, It's an engineering challenge that is being solved piece by piece, and with every solved problem, the far side becomes a little less terrifying. But the awe remains, because the far side is not just a place, it's a symbol. It represents the last physical frontier within our grasp. After the far side, the next step is Mars, then the asteroids, then the moons of Jupiter and Saturn. The far side is the gateway. And gates are always a little frightening. You don't know what's on the other side, but you step through anyway, because that's what explorers do. So when you look at the moon tonight, remember that half of it is hidden, and that hidden half is calling. It holds water that could sustain us. It holds silence that could teach us. It holds scars that record the violence of our solar system's birth. And it holds a challenge. Are we brave enough to go there? Not just to visit, but to stay? The answer is already forming in the labs of NASA, the workshops of SpaceX, the planning rooms of the China National Space Administration. The far side will be settled, not because it's easy, but because it's there. And because we are the species that doesn't stop. So the next time you hear someone say, "the dark side of the moon," smile. Politely correct them. Then tell them the truth. It's not dark. It's just waiting. And when we finally step onto its soil, we won't find monsters. We'll find ourselves. And that is the most terrifying and the most wonderful discovery of all. And so, as we stand on the edge of that final horizon, the threshold between the known and the unknown, we have to ask ourselves not just if we will go, but how we will carry that mirrored self with us. The far side is not a blank slate. It is a palimpsest written over by billions of years of impacts, solar wind, and the slow decay of radioactive elements. Every footprint we leave there will become part of that story. Every gram of ice we melt, every crater we drill, every radio telescope we plant will become a human inscription on a landscape that has never known life. That is a profound responsibility. Consider the moment of first contact, not with aliens, but with the soil itself. When the first astronaut steps off a ladder onto the far side, there will be no Earth in the sky, no blue marble to glance back at, no familiar point of reference. The stars will be the same stars we see from Earth, but without the moon's familiar glow washing them out. They will blaze with an intensity that no human eye has ever witnessed from the lunar surface. The Milky Way will stretch from horizon to horizon, a river of light undiluted by any atmosphere. And in that moment, the astronaut will be more alone than anyone in history, yet more connected to the cosmos than any human before. It will be a paradox that defines the far side experience, isolation that transforms into expansion. That first step will not happen tomorrow. It is still decades away. But the groundwork is being laid. NASA's Artemis program aims to return humans to the moon, initially to the south pole of the near side. But the architecture, the lunar gateway, the human landing system, the surface suits, is being designed with the far side in mind. A future Artemis mission could send astronauts into a distant retrograde orbit that takes them behind the moon, or even land them on the far side, using a relay satellite similar to China's Kuekiao. Private companies are also eyeing the far side. SpaceX's Starship, with its massive payload capacity, could deliver prefabricated habitats, drilling rigs, and rovers to the far side in a single launch. Blue Origin's Blue Moon lander could carry supplies. The infrastructure is being built, piece by piece, by a global coalition of space agencies and entrepreneurs. But with that infrastructure comes a chilling reality. The far side is a place where mistakes can't be fixed. On the near side, mission control can talk to astronauts in real time, a 2.5-second delay, manageable. On the far side, the delay is the same, but there is no direct line of sight. Even with a relay satellite, the signal must travel from Earth to the relay, then to the surface, and back. That adds latency, but more importantly, it creates a single point of failure. If the relay satellite fails, the far side base is cut off. Nobody on Earth can tell the astronauts what to do. They must be completely autonomous. That means they must have medical training, engineering skills, and psychological resilience far beyond what any previous crew has needed. They will need to perform surgery on themselves, repair their own life support, and make life or death decisions without guidance. That is a terrifying prospect. Yet humans have proven time and again that they can rise to such challenges. The Apollo 13 crew survived an explosion in space because they improvised with what they had. The crew of the International Space Station has handled emergencies with cool professionalism. The far side will demand that same mindset, but multiplied tenfold. The first settlers on the far side will be the most isolated humans in history. Their nearest neighbors will be 400,000 kilometers away, on the other side of a rock barrier that blocks all direct communication. They will live in habitats buried under meters of dust, breathing air, recycled from water mined from ice that has been frozen for 4 billion years. They will eat food grown in regolith, watered with melted ice, lit by LED arrays powered by a nuclear reactor humming beneath the surface. And they will look up, not at Earth, but at the Milky Way, and know that they are the vanguard of a new kind of humanity. That future is not guaranteed. It depends on continued political will, technological breakthroughs, and economic investments. But the seeds are planted. The far side is no longer a fantasy. It is a project. And like any project, it will be built in stages. The first stage is robotic reconnaissance. We have that already. The second stage is sample return. Chang'e 6 will provide that. The third stage is a robotic outpost, a small automated laboratory that can operate for years, drilling ice, analyzing soil, testing technologies. The fourth stage is a human-tended base, a place where astronauts can stay for weeks or months, conducting experiments and preparing for permanent settlement. The fifth stage is a colony, a self-sufficient community that can survive indefinitely. Each stage brings us closer to that moment when a human being places their foot on the far side soil. And when that happens, it will not be a single nation's achievement. It will be a milestone for our species. It will be the moment we prove that we can live beyond our home world, that we can thrive in the most hostile environments, that we can take our place among the planets. And yet, the far side will always hold secrets. No matter how many missions we send, there will always be craters too dark to explore, pockets of ice too deep to drill, magnetic anomalies we cannot explain. The far side is not a puzzle to be solved. It is a landscape to be lived with. It will challenge us, humble us, and inspire us. It will remind us that the universe is vast and we are small, but that smallness does not mean insignificance. It means we must be careful, curious, and brave. So, as this journey through the far side comes to a close, let us not think of it as an ending. Let us think of it as a turning point. The far side has been revealed, but it has not been conquered. It has been mapped, but not inhabited. It has been studied but not understood. The terror we feel when we look at those images of endless craters and eternal shadows is not terror of the unknown. It is the excitement of discovery. It is the anticipation of a new beginning. And that beginning starts now, not with a rocket launch, but with a shift in perspective. The next time you see the moon, whether it's a thin crescent or a full disk, remember that half of it is hidden. That hidden half is not empty. It is waiting. It is holding its breath. And one day, not too long from now, a human voice will break that silence. A human foot will disturb that dust. And a human eye will see the far side not through a camera, but directly, with wonder and awe. That will be the moment we finally understand what NASA really found on the moon's dark side. Not terror, but a mirror, a reflection of our own audacity, our own fragility, our own infinite capacity to dream. And in that reflection, we will see that the far side was never truly dark. It was just waiting for us to arrive. So go ahead, look up tonight. The moon is there, the far side is there, and so are we.
For billions of years, the moon quietly orbited the Earth, its far side hidden from view and untouched by human hands, until today. Even now, only machines touch its surface, revealing a world unlike what we thought we knew. China's Chang'e missions have uncovered the secrets of this unseen realm. Strange materials, ancient volcanic relics, and evidence of a history that challenges everything we thought we knew about our closest celestial neighbor. Did you know the two sides of the moon are fundamentally different? The side closest to us, with its smooth, dark plains, tells the story of ancient lava flows. In contrast, the dark side is a rugged, mountainous landscape untouched by volcanic forces. This stark dichotomy has puzzled scientists for decades, hinting at a violent and complex history. Now the stakes are higher than ever. Beneath the shadowed craters may lie the most valuable resource for humanity's future in space. Who will claim it, and at what cost? The coming decade promises change. Two nations, armed with unprecedented technologies, compete to define the future of lunar exploration. Will the next footprints on its surface signify a unified global effort, or the start of a new era of dominance? Although the moon is Earth's closest celestial companion, it's hard to imagine the difference greater than the contrast between its hemispheres. The near side, always facing our planet, feels familiar with its dark basaltic plains and cratered terrain. Conversely, the far side, hidden from view until space exploration began, is a rugged, mountainous landscape holding the secrets of the moon's evolution. China began exploring the moon relatively late, launching its first mission in 2007. This strategic delay allowed the country to build on advancements in space technology pioneered by others, leading to rapid progress. The Chang'e program, named after the Chinese moon goddess, embodies this deliberate approach. Each mission has made significant strides in technological capabilities and scientific understanding. In 2018, Chang'e 4 achieved an unprecedented milestone: the first soft landing on the moon's far side. This region, hidden from Earth's view, had never before been explored from the lunar surface. The accompanying rover, U-22, began traversing the rugged terrain of the Van Karman crater. Early in its mission, it discovered an unexpected gel-like material in a small crater. While initial analysis suggested it might be impact glass from a meteorite, the finding hinted at geological complexities on the Moon's less explored hemisphere. Additionally, the Chang'e 4's spectrometer provided critical data, including samples thought to originate from the Moon's mantle, intriguing lunar scientists worldwide. Launched in late 2020, Chang'e 5 marked China's first attempt to transport samples from the Moon back to Earth. The spacecraft performed a flawless series of maneuvers. It landed in the Oceanus Procellarum, collected over 4 pounds of lunar material, and launched the samples back to Earth. Robotic arms extracted material from both surface and subsurface layers, offering an instant snapshot of the Moon's history. These samples, younger than those collected during the Apollo missions, provide evidence of prolonged volcanic activity in specific regions, reshaping our understanding of the Moon's thermal evolution. The mission's achievements extended beyond science. The docking of the lander with the orbital module in lunar orbit was the first fully robotic docking performed beyond Earth. Building on previous successes, Chang'e 6 set its sights on the Moon's far side, specifically the Apollo crater. In mid-2024, the mission returned the first-ever samples from this enigmatic region. Initial analysis revealed striking differences in the composition of the far side's regolith compared to the near sides. These samples, with lower density and a unique mineral composition, suggest they were shaped under the influence of distinct geological and impact processes. The discoveries made by Chang'e 6 shed light on the mysteries of volcanic activity, collision history within the inner solar system, and even the early composition of the Moon's crust. Additionally, its successes paved the way for future missions, including a proposed landing with crew at the Moon's south pole by 2030. But more on that later. And so the samples returned by Chang'e missions, particularly from the Moon's far side, have provided unprecedented insights into the Moon's formation and early geological activity. The dark plains on the near side, known as lunar mare, owe their existence to ancient volcanic activity. These regions are rich in potassium, rare earth elements, and phosphorus, collectively referred to as creep. Creep materials, believed to have formed during the Moon's early differentiation, are a hallmark of its volcanic history. These elements suggest a time when internal heat drove magma to the surface, forming the smooth plains visible today. In contrast, the far side is dominated by rugged terrain and a thick crust. Samples collected from the Apollo crater and other regions show a lower concentration of creep materials. This asymmetry indicates that the Moon's internal heat distribution was uneven, possibly due to tidal interactions with Earth during its early formation. These findings align with theories suggesting a massive impact on the far side created the South Pole Aitken Basin, redistributing materials and heat across the Moon. One of the most groundbreaking discoveries is a basalt fragment, dating back approximately 4.2 billion years. This ancient rock, retrieved from the Moon's far side, offers a direct glimpse into its volcanic past. The fragment contains a unique mineral composition, hinting at a volcanic activity vastly different from that on the near side. Unlike the expansive lava flows seen on the near side, volcanic events on the far side were far more localized and less intense. This discovery challenges assumptions about the Moon's thermal history. While the thin crust on the near side facilitated widespread volcanic activity, the thicker crust on the far side likely acted as an insulator, limiting the extent of eruptions. Isotropic analysis of the basalt fragment also hints at the presence of water in the Moon's interior during its early history. The rugged appearance of the far side and the absence of extensive maria can also be attributed to its collision history. Craters on the far side, such as Apollo crater, preserve evidence of asteroid impacts that occurred billions of years ago. The lack of widespread lava flows on this side allowed these impacts to remain relatively intact, providing an untouched record of the early bombardment phase of the solar system. Samples from these craters reveal an abundance of light-colored materials, such as feldspar, a key component of the Moon's crust. This contrasts sharply with the darker basalt-rich samples from the near side. The presence of feldspar, along with more porous and friable structure, supports the hypothesis that the far side's crust was less affected by processes of interim melting and resurfacing. The stark differences between the Moon's hemispheres may also be rooted in its very formation. The prevailing theory, known as the giant impact hypothesis, suggests that the Moon formed from debris resulting from a collision between Earth and a Mars-sized body called Theia. The uneven distribution of heat and materials during this chaotic period likely set the stage for the observed asymmetry. The lower concentration of creep elements on the far side aligns well with this theory. As the molten Moon began to cool, denser materials may have migrated to the near side, under Earth's gravitational pull. This process, known as tidal heating, could explain why the far side remained geologically distant and less active. The discoveries made on the Moon's far side illuminate critical planetary formation processes that extend beyond our satellite. Understanding the Moon's dichotomy helps refine models of the evolution of rocky planets and their moons, including Earth itself. As new missions continue to explore the Moon, each collected sample brings humanity closer to unraveling the mysteries of our closest celestial neighbor. Let's take a look at the Artemis program, for example, which represents humanity's ambitions to return to the Moon, but this time for sustained exploration and as a gateway to Mars. However, the realization of such an ambitious plan faces significant obstacles. Delays caused by technical issues, financial constraints, and dependence on private industry. The Orion capsule, the crew component of Artemis, has faced repeated delays due to issues with the European-built service module and software integration. During testing, discrepancies were found in navigation systems and life support functions, which are crucial for astronaut safety. These complications have resulted in the launch of the Artemis II spacecraft, which is supposed to orbit the Moon, being pushed back to 2026. At the same time, SpaceX's lunar spacecraft with the name of Starship, a critical element for the first Artemis III landing on the Moon, is still behind schedule. The vehicle is struggling to meet NASA's strict safety and performance requirements, including successful high-altitude and landing tests. The size of Starship, designed to deliver astronauts to the lunar surface, creates unique challenges when integrating with a smaller Orion capsule and the Gateway space station. Moreover, the Artemis program heavily relies on public-private partnerships through initiatives like Commercial Lunar Payload Services, CLPS. While this collaboration fosters innovation and cost reduction, it also places private companies at the mercy of timelines and risk management strategies. Recent failures, such as the Peregrine lander by Astrobiotic and the IM-2 mission by Intuitive Machines, highlight the challenges associated with outsourcing critical components. Despite these setbacks, the CLPS initiative serves as a testing ground for technologies needed for the Artemis program. Autonomous landing systems, lightweight materials, and modular spacecraft designs tested during these missions are paving the way for safer human landings in the future. The experience gained during these efforts is invaluable, even if it comes with delays. The progress of the Artemis program is further complicated by political uncertainty, shifts in administration priorities, budget fluctuations, and competing domestic issues often lead to schedule shifts. With an annual budget of $24 billion, NASA must allocate funding between the Artemis program, planetary science missions, and the International Space Station. Dependence on private companies adds another layer of complexity, as their profitability and corporate strategies can directly impact mission schedules. And let's not forget about the public enthusiasm for space exploration, which plays a significant role in funding decisions. While Artemis aims to evoke the same awe and wonder as Apollo, the high cost of lunar exploration, about $1 million per kilogram of payload to the moon, raises questions about its economic justification. NASA's leadership must constantly advocate for the long-term value of the program, emphasizing its potential to create a sustainable lunar economy and deepen scientific knowledge. The challenges of the program remind us of the early stages of the Apollo project, marked by constant failures and lessons learned. Still, as NASA and its partners work to refine technologies and operations, the program is laying the foundation for a new era of human space exploration. The 21st century space race between China and the U.S. represents a new chapter in the quest for lunar dominance. Unlike the Cold War-era race, driven by ideological rivalry, this competition is defined by strategic ambitions, economic potential, and scientific research. At the forefront of this race are contrasting approaches: China's methodical and centralized program versus the U.S.'s collaborative but complex public-private structure. China's lunar program is characterized by steady, incremental progress. Each mission builds upon the previous one, advancing both technical expertise and scientific results. After Chang'e 6 has already achieved significant success in returning samples from the far side, China's ambitions now extend to establishing a permanent presence on the moon. By 2030, the country plans to land astronauts at the moon's south pole, a region of great interest due to the presence of water ice in permanently shadowed craters. The centralized approach of the Chinese government allows for streamlined decision-making and concentrated funding. The program benefits from long-term planning, with space exploration prioritized as a strategic goal. Additionally, a well-developed network of lunar relay satellites ensures reliable communication and navigation, which is crucial for operations of the South Pole. Moreover, China has expressed interest in developing the international partnerships for its lunar missions, particularly with countries in Asia, Africa, and Europe. While this collaboration is limited compared to NASA's extensive global partnerships, it enhances China's influence in shaping the future of space exploration. In contrast, U.S. lunar ambitions rely on collaboration between NASA and private companies. This public-private model has fostered unprecedented innovation, ranging from reusable rockets to autonomous landing systems. However, it also creates challenges, as discrepancies in timelines, priorities, and resource allocation can lead to delays. Unlike China's centralized system, NASA must navigate fluctuating political landscapes and competing interests from its commercial partners. While this approach promotes technological breakthroughs, it requires careful coordination to align missions with broader strategic goals. One of the advantages of the American approach is its focus on sustainability. The Gateway Lunar Station and the proposed LunaNet communication system are designed to lay the groundwork for continuous research. These projects aim to support not only Artemis missions, but also future international and commercial endeavors, strengthening the U.S.'s leadership in space exploration. The South Pole is a critical location in the lunar race. Its deposits of water ice are invaluable for sustaining human presence and producing rocket fuel. Control of this region could provide significant strategic and economic advantages, making the moon a stepping stone for deeper space exploration. However, the complex terrain and extreme environmental conditions will pose a real test for both countries' capabilities. The renewed focus on the moon has raised concerns about the potential monopolization of lunar resources and the broader consequences of the competitive space race. As China and the U.S. pursue their lunar ambitions, questions arise about the balance between cooperation and competition, as well as the strategic significance of lunar exploration in an increasingly polarized global landscape. A resource like water ice is not only essential for sustaining human life, but also holds potential for in situ utilization, including the production of hydrogen and oxygen for fuel. Control over these deposits could offer significant economic and strategic advantages. China's targeted approach, with missions like Chang'e 6 aimed at scientifically and economically valuable regions, raises concerns about exclusive access. By steadily developing its lunar potential, China may position itself as the primary extractor and distributor of these resources. Given the lack of comprehensive international frameworks for distributing lunar resources, this scenario has sparked discussions about the need for new governance mechanisms to prevent monopolization. Existing treaties, such as the 1967 Outer Space Treaty, prohibit sovereign claims on celestial bodies, but they do not adequately address the commercialization of resources. The potential dominance of one party in mining lunar ice and minerals could change these frameworks, prompting nations to reconsider the rules for space exploration and resource use. Despite the rivalry, recent events hint at opportunities for cooperation. The provision of lunar samples from the Chang'e 5's mission to American researchers marks a step towards scientific diplomacy. By sharing findings and fostering mutual understanding, such exchanges could ease tensions and pave the way for broader cooperation. Historically, science has bridged divides between warring nations. Even during the Cold War, the U.S. and the Soviet Union exchanged samples, contributing to breakthroughs in planetary science. Such cooperation can only benefit research and potentially lead to the establishment of international norms for resource use. The moon is not just a scientific frontier, it's a platform for broader strategic ambitions. Whether it's resource extraction, technological development, or geopolitical influence, the actions taken in the coming years will shape humanity's presence in space for decades to come. The balance between competition and cooperation remains essential to ensure that the moon becomes a shared resource for all of humanity. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's South Pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's South Pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? do earthquake-like tremors shake this silent world. And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the Moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the Moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the Moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The Moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the Moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the Moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the Moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the Moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the Moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the Moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the Moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity. It's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's South Pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. His role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. For centuries, humanity has looked to the sky, wondering if other worlds exist beyond our own. But now we know that among the surrounding stars, there are planets orbiting them. Some are massive giants, locked close to their stars. Others lie in the shadows, far enough away to remain cold and hidden. And yet, even among thousands of discoveries, there are a few worlds close to us. Close enough to imagine we could reach them. These nearby planets are not just glowing dots. They are clues, bringing us closer to answers to questions that once seemed impossible. Could any of these worlds harbor life? How similar or alien might they be? The search for exoplanets has transformed from myth to method. And now the question is not whether other worlds exist, but how many there are, and what secrets they might hold. Our story begins in 1995, when 51 Pegasi b became the first planet discovered orbiting a star similar to our Sun. A discovery that shook the foundations of astronomy. For centuries, we wondered, do other worlds exist beyond our planet? Early science fiction writers imagined distant planets suitable for life, while scientists endlessly speculated. But until this moment, planets outside our solar system existed only in our imagination. The answer, however, was hidden in the silent motion of stars, detectable only through new technology. Swiss astronomers Michel Mayor and Didier Queloz, leading a team equipped with powerful spectrographs, found the first signs of an exoplanet orbiting a sun-like star in the Pegasus constellation. They announced that there was indeed a massive gas giant, similar to Jupiter, but orbiting much closer to its host star, completing an orbit at an astounding speed every 4 days. This discovery was made possible by observing a wobble in 51 Pegasi, a tiny but noticeable shift in the star's position caused by the gravitational pull of an unseen companion. The radial velocity method used here, with great success, allowed scientists to measure this minuscule shift in starlight, somewhat like a faint drumbeat in a distant room. It's a subtle vibration we can sense but not see. The radial velocity method enabled scientists to detect this heartbeat of the star, concluding the presence of a planet by analyzing regular oscillations in its spectral data. This discovery wasn't just proof that other planets exist, but proof that we could find them. For the first time, the scientific pursuit of planets outside the solar system stopped being purely speculative and transformed into a tangible search. This discovery shed light on an entirely new field of astronomy, planetology. However, for some of our erudite viewers, a very logical question may arise. Was 51 Pegasi b truly the first observed exoplanet? Well, it's a good question, and the answer is nuanced. Pegasi b was the first confirmed exoplanet found orbiting a sun-like star in 1995. However, it was not the first exoplanet ever observed. In fact, the first confirmed exoplanet was discovered orbiting an entirely different type of object, a pulsar. In 1992, astronomers Alexander Wolfstan and Dale Frail discovered 2 planets which were given evocative names, Poltergeist and Phobiter. However, these planets orbited a rapidly spinning neutron star, Lich, named after a powerful fictional undead creature, since it made their environment vastly unlike any conceivable planetary systems with conditions far too hostile for life as we know it. Thus, Pegasi b received special recognition because it was the first confirmed exoplanet orbiting a sun-like star, suggesting that planets could exist in environments more familiar to us. This discovery sparked a wave of exoplanet research focused on stars that might resemble our solar system. Beyond confirming the existence of exoplanets, the discovery of 51 Pegasi b expanded our understanding of their diversity. How could a gas giant form so close to a star without being engulfed? Well, until then, many astronomers believed that only small, rocky planets, like Earth, could orbit a star up close. And this hot Jupiter made us rethink models of planetary system formation. Along with it, the search for planets turned from an isolated theory into one of the most dynamic areas of discovery in modern science. A year after the previous discovery, astronomers found another exoplanet, this time around 47 Ursae Majoris, a star located 46 light-years away and surprisingly similar to our Sun. But this discovery was different. While Pegasi b was a hot Jupiter, orbiting very close to its star. Ursae Majoris b had an orbit much farther away, with an impressive orbital period of nearly 3 years. In other words, this planet orbits its star at a distance similar to the gas giants in our solar system, making it the first long-period exoplanet found around a main-sequence star. This discovery was significant as it hinted at cosmic order beyond our own system, suggesting that our solar system structure might not be unique. But finding it was no easy task. Unlike close-orbiting planets, which can be detected with relatively short-term observations, Ursae Majoris b required meticulous, repeated measurements over a long period. For nearly 9 years, astronomers had to observe the faint wobbles of the host star's light, tracking each tiny shift, every hint pointing to a hidden planet. Yet, with each observed light shift, astronomers moved closer to the proof they sought after. This discovery gave way to new hypotheses that planets could form and maintain stable orbits in many types of star systems, expanding the scope of exoplanet studies. Realizing that distant star systems could mimic the arrangement and order we see in our system prompted astronomers to consider the possibility of planet formation in a vast range of conditions, from the outskirts of red dwarfs to the expanses around yellow stars like our own. A couple of years later, in 1998, astronomers discovered Gliese 876b, an exoplanet orbiting a star twice as close to us as any previously discovered, at a distance of just 15 light-years. This wasn't just another distant point of interest, it was a potential neighbor in the infinite cosmos. And this discovery added a new level of tangibility to exoplanet research, suggesting that planets exist not only somewhere out there in an abstract sense, but much closer than we could have imagined. However, this exoplanet also posed a unique challenge. It orbits a red dwarf, a type of star with properties vastly different from our Sun. Red dwarfs are smaller, dimmer, and cooler. For years, astronomers doubted that these stars could be hosts to planets, especially large ones. A gas giant orbiting close to a red dwarf once again defied existing theories of planet formation, pushing scientists to rethink and adapt their understanding of where and how planets might form. Initially discovered through the combined efforts of the W.M. Keck and Lick observatories using the radial velocity method, Gliese 876b turned out to be a massive gas giant. Its existence confirmed by observing the faint wobble of its parent star. This back-and-forth motion caused by the gravitational pull of its unseen planet showed that the red dwarf was indeed significantly influenced. To collect precise data on the planet's mass, astronomers employed an astrometric technique using the Hubble Space Telescope, an unprecedented method that enabled researchers to receive highly accurate mass measurements. Using Hubble's fine guidance sensors, a specialized instrument typically used for telescope aiming and stabilization, a team led by George Benedict and Barbara MacArthur measured the side-to-side wobble of Gliese 876. Over the course of 2 years, they meticulously mapped this small shift, comparable to the size of a quarter, viewed from 3,000 miles away. These measurements revealed that the planet's mass is 2 to 2.5 times greater than Jupiter's, which allowed them to classify it as a low-mass gas giant, and the first exoplanet whose mass was confirmed through astrometry. These precise measurements allowed astronomers to confirm that the planet orbits its star at an inclination nearly identical to Earth's, a crucial detail for determining mass accuracy. Hubble's astrometric confirmation marked a significant advancement, establishing a method later used for confirming dozens of other exoplanets. This uncovered a new era of precision in mass and orbit determination. Meanwhile, let's jump to the year 2000, to the discovery of Epsilon Eridani b. It was a milestone that showcased the increasing sophistication of methods used for searching for planets and underscored the need for precision in astronomical measurements. This exoplanet was later given its own name, Aegir, representing the ancient Norse sea god. According to mythology, Aegir is married to the goddess Ran, who also represents the sea. Thus, the star Epsilon Eridani received her name. Aegir is a gas giant with a mass about 80% that of Jupiter, orbiting at a distance of roughly 3.5 astronomical units from its host star. It takes Aegir about 7.6 years to complete one orbit. Detecting it was a challenging endeavor. It took decades worth of data, and the scientific community was highly skeptical due to the complex behavior of the star itself. The early signs of a planet orbiting the star transpired in the early 1990s, led by a Canadian team using Doppler spectroscopy. However, initial observations were too vague to confirm the planet's presence, leaving room for doubt. The magnetic activity of the star complicated the data, creating Doppler noise that made it difficult to isolate the gravitational influence of the planet. Years of collected data and method refinement were required before a team led by Artie Hatzis could definitively confirm the existence of Epsilon Eridani b in 2000 using the Doppler shift, a method sensitive enough to detect subtle changes in the star's velocity. In 2006, astronomers took another step forward in regards to confirming the existence of Aegir. Using astrometry with the Hubble Space Telescope, under the guidance of George Benedict and Barbara MacArthur, who we met earlier. The team measured the star's minuscule side-to-side wobble. The astrometric technique was sensitive enough to accurately determine the gravitational pull of the planet toward Epsilon Eridani and provide a more precise estimate of its mass. These observations showed that the exoplanet's orbit was inclined nearly edge-on to Earth, meaning the planet's orbital plane around its star almost aligns with our line of sight, which in turn tells us that the planet pulls its star directly toward and away from us in a measurable way, making the detection of Doppler shifts in the starlight especially effective. Scientists initially concluded that Aegir's mass is approximately 1.5 times greater than Jupiter's, although later refinements placed it closer to 8% of Jupiter's mass. However, the process was still far from simple. Observations using the Spitzer Space Telescope in 2006 discovered an asteroid belt near the orbit of Epsilon Eridani b, raising concerns about the stability of its orbit. Had the planet's orbit been as eccentric as initially suspected, it would likely have destabilized or disrupted the asteroid belt. This led scientists to reassess the eccentricity of the orbit. Further studies published between 2019 and 2022 revealed that Aegir likely has a nearly circular orbit with an eccentricity close to 0.07, which stabilizes its movement within the asteroid belt. Despite these findings, Epsilon Eridani b remains challenging to observe directly. Attempts to capture its image using the Sphere instrument on the Very Large Telescope in 2019 and 2020 did not confirm observations, even after more than 38 hours of exposure over 12 nights. These difficulties underscore the limitations of existing technology in detecting low-luminosity exoplanets, particularly those orbiting dim stars like this one. Today, with the extended infrared capabilities of the James Webb Space Telescope, astronomers hope to finally obtain a direct image of Hygiea, which could reveal new details about its atmosphere and composition. The story of this discovery vividly demonstrates the importance of precision, long-term data collection, and continuous technological advancement for understanding exoplanets. The next milestone in exoplanet science was the discovery of Proxima Centauri b in 2016. Orbiting the star closest to our Sun, only 4.25 light-years away, this planet became the closest known exoplanet to us. Proxima Centauri b immediately drew astronomers' attention to its Earth-like characteristics: a similar mass, and an orbit within the habitable zone of its star, a region where temperatures could allow for liquid water. This combo of proximity and potential habitability made its discovery historic, sparking enormous excitement and hope in the scientific community. This discovery was the culmination marking years of focused, long-term observations under the Pale Red Dot Project. Launched specifically to detect an exoplanet around Proxima Centauri, the project represented a substantial collaborative effort, with astronomers worldwide meticulously monitoring tiny changes in the star's light. By tracking minuscule Doppler shifts caused by the gravitational pull of the planet, scientists confirmed its existence and some characteristics. The success of the Pale Red Dot Project stands as a testament to the dedication of astronomers who, despite the challenge of detecting such faint signals, remained unwavering in their commitment to finding nearby worlds. These observations took several years and required extremely precise measurements, as the star's own flares and activity complicated the data. In the end, the team's hard work paid off, proving that not only did this planet exist, but also the fact that it was close enough for in-depth study, possibly even with direct imaging in the near future. Due to its proximity to Earth and potential habitability, Proxima Centauri b has become a prime candidate for future exploration. The possibility of studying it up close, or even sending an interstellar probe there, has stirred discussions among scientists and engineers worldwide. Projects like the Breakthrough Starshot Initiative propose sending ultralight nanocrafts moving at the speed of light, propelled by powerful laser beams, to reach the system within decades. These probes could capture the first images of the planet, revolutionizing our understanding of exoplanetary environments. In just a few decades, we've gone from the first signs hinting at planets beyond our solar system to a catalog containing hundreds of worlds, each one showcasing the diversity of planets within our galaxy. Every nearby exoplanet we've discovered works toward deepening our understanding of what makes a planet unique and what could make it habitable. As technology advances, we're getting even closer to direct observations and the tantalizing possibility of exploring these worlds up close. From detecting distant wobbles to imagining interstellar probes, our search has transformed the night sky into a map of possibilities, bringing us closer to understanding our place in the cosmos. Today, exoplanets inspire not only our questions, but our ambitions, pushing us toward a future where discovering our neighbors in space is more than a dream. It's our next frontier. Beneath the surface of our everyday lives, governed by the familiar pull of gravity and the invisible bonds of electromagnetism, lies a hint of something more. something that challenges the established order of forces that shape our reality. For centuries, the human intellect has tried to make sense of the majestic diversity of nature, unraveling thread by thread the laws that govern all things visible and invisible. And yet, as we look ever deeper into the heart of matter and the vast expanse of space, we are increasingly confronted with anomalies, behaviors that defy explanation, phenomena that slip through the cracks of our most trusted theories. This is where the rumor of a fifth force, a force beyond gravity, electromagnetism, and nuclear interactions, originates. So, today we decided to ask, how possible is the existence of this fifth architect of the universe, forming the very essence of matter and energy? First, let's start with the basics to make sure we're all on the same page. 4 fundamental forces are at work in the vastness of the universe, each playing its unique role, shaping everything from the microcosm of subatomic particles to the macrocosm of galaxies. Gravity, often considered the force most familiar to us, dictates the motion of planets and stars, causing celestial bodies to move in their orbits. It's the same force that keeps our feet on Earth and makes apples fall from the tree. Next, we'll look at electromagnetism. This force is responsible for the glow of auroras, the brilliance of stars, and the very light traveling through the vastness of space to meet our eyes. Electromagnetism controls the interaction of charged particles, creating everything from palpable warmth of sunlight to the invisible waves that carry our voices through the air. Another force at the heart of every atom is the strong nuclear force. It reigns supreme within the atomic nucleus, ensuring protons and neutrons remain locked in a strong bond. This force is the reason for the existence of the glowing crucible of the sun and the grandest explosions in the universe supernovae. Although limited in range, it is the key to the power of stars, driving thermonuclear reactions. Finally, we encounter the weak nuclear force, a subtle shaper of the elements. The weak nuclear force plays a crucial role in the nuclear processes that power stars and lead to the synthesis of various elements. This force is necessary for the sun to shine and for the very existence of elements beyond hydrogen in the periodic table. These 4 forces describe the complex interaction of matter and energy that dictates the universe's structure, behavior, and evolution. Understanding them is essential to understanding the fundamental principles governing our world. In the realm of infinitesimals, where atoms are their universes, 4 fundamental forces manifest their influence uniquely. The strong and weak nuclear forces acting within the atomic nucleus are central to this scale. The strong nuclear force, with its iron grip, ensures the stability of the atomic nucleus. This force is so powerful that it overcomes the repulsion between positively charged protons, binding them with neutrons to form the nucleus, the heart of every atom. Though powerful, this force is remarkably short-ranged. Its influence barely extends beyond the nucleus. Meanwhile, the weak nuclear force makes itself known through beta decay, transforming a neutron into a proton, while emitting an electron and an antineutrino. Although weaker and short-lived than the strong nuclear force, this force plays a key role in the alchemical transformations within stars, helping to synthesize the elements that make up our world. Translating our view of the celestial interaction of planets and stars, gravity and electromagnetism begin to dominate the scene. Overarching gravity governs the orbits of planets around stars, holds moons bound to planets, and gives structure to galaxies. Electromagnetism, on the other hand, is the architect of light. From the violent flares of the sun to the serene glow of distant stars. This force generates the entire electromagnetic spectrum, from radio waves to gamma rays, providing the visibility of the cosmos and the fundamental interactions between charged particles in its vastness. On the largest scales of galactic superclusters, gravity is the undisputed ruler. It weaves together the fabric of the cosmos and dictates the motion of galaxies and the structure of the universe itself. However, things have become much more complicated than we previously thought. Scientists continue to encounter phenomena that defy our established quartet of forces. These anomalies suggest the existence of a force beyond gravity, electromagnetism, and nuclear interactions. One such mystery arose in the bowels of particle physics. In the late 20th century, experiments designed to investigate the characteristics of fundamental particles began to reveal inconsistencies. Measurements of the decay rates of some particles and the gravitational behavior of objects on microscopic scales hinted at effects not accounted for by the standard model of particle physics. Even pioneers such as Ettore Majorana and Julian Schwinger suggested the existence of additional forces, and their theories offered the first mathematical framework to account for these anomalies. Schwinger, in particular, proposed a fifth force with a small radius of action that could subtly influence the interaction of particles and yet be undetectable in broader gravitational measurements. Subsequent studies highlighted several anomalies that current theories of physics cannot fully explain. A reanalysis of the Ethos experiment by Professor Fishback and his colleagues back in 1986 revealed inconsistencies in gravitational acceleration that depended on the composition of materials, indicating non-Newtonian coupling. Similarly, in the 1996 revisit by Fishback and Talmage, the motivation for studying the fifth force was the recognition that some experimental results could not be explained by known forces, including gravitational anomalies and deviations in kaon regeneration experiments that hinted at an anomalous energy dependence that could arise from an external field. The initial speculation around the fifth force was driven mainly by a desire to explain these anomalies. The hypothesis suggested the existence of a new medium-range force, similar to gravity, arising from the exchange of a new ultralight boson. This boson was based on numerous Planck scale theories predicting such bosonic fields, altering the usual gravitational interaction between masses. Subsequent studies aimed to find new theories and hypotheses to explain the observed anomalies and further test the fifth force hypothesis. They consider the influence of a massive hypercharge field, proposing the exchange of hyperphotons to create a potential that could explain the anomalies observed in the Ethos experiment. Despite the lack of conclusive evidence for such a force, continuing anomalies in the experimental data and the predictions of various unifying theories leave the search for a fifth force an open question. The search for a fifth power has gained new momentum in recent years. The Atomki experiment, led by scientists from the Hungarian Academy of Sciences, has revealed one of the most tantalizing hints. Observing an unexpected anomaly in the decay of beryllium-8 atoms suggested the influence of a force not predicted by existing theories, a potential carrier particle called the X17 boson. This discovery has sparked a flurry of theoretical work, with physicists worldwide proposing new models to explain the Atomki anomaly and similar observations. Theories involving dark photons, photophobic forces, and hidden sectors of the universe have emerged, each trying to weave these anomalies into a coherent narrative. Around the world, advanced research centers have become springboards for this monumental quest. From the vast CERN complex, home to the colossal Large Hadron Collider, to the intricate underground labyrinths that house the ultra-sensitive detectors of the Lux Zeppelin dark matter experiment, These are modern temples of science. Here, amid the hum of superconducting magnets and the soft glow of computer screens, physicists push the boundaries of the known universe. At the heart of the LHC, amid a maze of tunnels and the hum of accelerating particles, scientists explore the fabric of reality. Here, particles accelerate to near-light speeds and then collide, giving birth to a fleeting microcosm where the laws of physics can be observed in their most primal form. In these high-energy collisions, signs of the fifth force, unveiled in the consequences of subatomic interactions, may lurk. One experiment that shook up conventional wisdom was the observation of anomalous decay of B mesons in the LHCb experiment. These mesons, consisting of a lower quark bound to a lighter quark, exhibited a decay pattern that deviated from the predictions of the Standard Model. Decay into electrons and muons, particles that should be treated equally by the known forces, showed an unexpected bias. This discrepancy hinted at an unseen influence, perhaps the bearer of a new force, subtly altering the behavior of fundamental particles. On the other side of the Atlantic, Fermilab has embarked on a search using the muon G-2 experiment. Similar to heavy electrons, muons have a magnetic moment, a property that dictates how they interact with magnetic fields. The Standard Model of particle physics, a theory that's withstood the scrutiny of countless experiments, predicts this magnetic moment with surprising accuracy. However, the muon G-2 experiments measured a value that stubbornly disagrees with these predictions. This deviation suggests that muons may be feeling the attraction of an unknown force whose influence eludes our current understanding. The centerpiece of this experiment is the muon, an elementary particle similar to an electron, but with about 200 times the mass. These particles constantly bombard the Earth as a byproduct of cosmic rays striking the atmosphere, making them both ubiquitous and valuable for scientific research. The muon G2 experiment is based on the desire to accurately measure the anomalous magnetic dipole moment of the muon, often referred to as the G2 value. This physical quantity reflects the oscillation or precession of the muon under the influence of a magnetic field. The Standard Model of particle physics, the most reliable framework for understanding the fundamental forces and particles of the universe, offers accurate predictions for this quantity. However, if experimental measurements deviate from these predictions, this may indicate the influence of forces or particles beyond our current theoretical picture.
The magnet used for the muon G-2 experiment is a superconducting magnet. It has a 50-foot diameter. We run more than 5,000 amps through it, which produces a field of approximately 1.45 Tesla, which is about 30,000 times the magnetic field of the Earth. So it's a very strong magnet.
Inside this magnet, muons are trapped and observed as they cross the magnetic field. However, despite all their power, muons embody the ephemeral nature of the subatomic world. They live only 2.2 microseconds before decaying into electrons and neutrinos. This short lifespan of 2 millionths of a second is a blink of cosmic time. But it is just long enough for physicists to make measurements. By meticulously measuring the precession rate of muons, scientists can compare experimental results with theoretical predictions derived from the Standard Model. The first results of Fermilab's muon G2 experiment, published in April 2021, have aroused the scientific community's interest. The measured precession rate of muons showed a significant discrepancy with the predictions of the Standard Model. In particular, the muons oscillated at a higher rate than expected, suggesting the possible influence of unknown particles or forces interacting with the muons. This discrepancy, expressed as a deviation with a statistical significance of 1 in 40,000, means there is a 99.9975% chance that this result is not a simple statistical fluke, but a tangible sign of new physics. The implications of the results of the muon G2 experiment extend far into the realm of cosmology and particle physics. If the observed discrepancy is confirmed, it could provide insight into the pervasive mysteries of dark matter, dark energy, and the imbalance between matter and antimatter. In a nutshell, dark matter, which makes up approximately 85% of the matter in the universe, remains undetected in direct experiments and is known only through its gravitational effects on cosmic structures. Similarly, dark energy, which drives the universe's accelerated expansion, accounts for only 74% of its energy content, and its nature is largely unknown. The asymmetry of matter and antimatter, in turn, raises the question of why the universe is dominated by matter. Despite theoretical predictions of equal amounts of matter and antimatter at the origin of the universe, the results of the muon G2 experiment may hint at new particles or interactions affecting the behavior of the muon, which may be related to the elusive dark matter or other unknown aspects of the universe. In addition, these results may help study antimatter and the asymmetry between matter and antimatter, shedding light on the conditions that led to the predominance of matter in the universe. In the context of the past successes of the Standard Model, the G2 muon experiment represents a turning point in the ongoing quest to understand the universe's fundamental structure. The Standard Model has had a profound impact on modern physics, providing significant technological advances and deepening our understanding of the structure of the universe. Can such experiments illuminate the mysteries of dark matter, dark energy, and the asymmetry of matter and antimatter? The G2 muon experiment could herald a new chapter in our understanding, guiding us toward a more complete theory of the universe. We look forward to further research and confirmation of experiments by scientists in this fundamental area of physics. Imagine a colossal invisible force at the galaxy's heart, controlling its existence. This hidden conductor is none other than a supermassive black hole. Although they're often portrayed as chaotic, all-consuming monsters, these giants play a crucial role in the life cycle of galaxies. At the center of most large galaxies is a supermassive black hole whose gravitational pull is so strong that not even light can escape it. However, they actually do more than just absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways that are only beginning to be understood. Recent research shows that the jets of gas and radiation ejected from the poles of supermassive black holes are akin to the airways that feed our lungs. These jets create shock waves that oscillate, much like the thoracic diaphragm in our chest cavities, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from getting too big and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how a galaxy's heart and lungs in the form of gas plumes from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be filled with zombie galaxies, huge clusters of dead or dying stars. The shock waves generated by black hole jets can prevent star formation by heating the surrounding gas, preventing it from cooling and condensing into new stars. This process may seem destructive, but it's necessary to maintain the health and longevity of galaxies. Today, we'll try to understand the mysterious nature of supermassive black holes, learn the profound impact they have on the universe, and by the end, we'll realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass of about 8 to 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar mass black hole. Such black holes usually have a mass several times that of the Sun. Another way is the direct collapse of massive gas clouds, which completely bypasses the star formation stage. This process can lead to the formation of black holes with masses from thousands to hundreds of thousands of solar masses. Such direct collapses are thought to have occurred in the early universe and were the seeds of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of Einstein's general theory of relativity. These equations describe how matter forms the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape it. The first black hole confirmed by observations was Cygnus X1. Discovered in 1964, this stellar mass black hole in the Milky Way was identified by X-ray emission that was caused by the accretion of material from a companion star. This discovery was the first convincing evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the boundary beyond which nothing can go once within its limits. The photon sphere is a region where gravity is so strong that light particles are forced to orbit. In the center, there is a singularity, a point of infinite density where the laws of physics known to us are destroyed. Black holes come in a variety of sizes. Stellar mass black holes are formed from collapsing stars and have masses several times that of the Sun. Supermassive black holes, located at the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, which are less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration has captured the first ever image of a black hole located in the galaxy M87. In this historic image, the black hole's shadow can be seen against a glowing accretion disk. The observation provided direct visual confirmation of theories about black holes and opened new possibilities for studying these mysterious objects. One of the most common and debated questions about black holes lately is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon, one falling into the black hole and the other flying out. Over an incredibly long period, this trickle of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are portrayed in science fiction, they're not cosmic vacuum cleaners that indiscriminately suck up everything around them. To hit them, objects must come incredibly close to the event horizon. In addition, although black holes have been proposed as potential wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the basics of black holes, how they form, their different types, and key discoveries lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is felt due to the enormous gravitational forces they exert on their surroundings. But how do these colossal formations arise, and what are their defining characteristics? Theoretically, a black hole is formed when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that it cannot escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive black holes, are scattered throughout the universe, and their number may be in the billions. Supermassive black holes with masses millions or billions of times that of the Sun are detected due to their gravitational influence on nearby stars. These stars orbit around the black hole much faster than they would around a normal object of similar size. Measuring these orbital velocities, astronomers can estimate the mass of the black hole. For example, the black hole at the center of our Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Some supermassive black holes exceed even Sagittarius A. The dwarf galaxy Leo 1 is home to a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with a staggering mass of 55 million solar masses. And even more colossal is a black hole in the Abell 2261 galaxy cluster, estimated to have a mass of about 100 billion solar masses, although its exact location remains unspecified. These black holes, especially in active galaxies, behave differently. Surrounded by an accretion disk of rapidly spinning gas and dust, they can emit huge amounts of energy, sometimes outshining their entire galaxy. This very process was famously captured by the Event Horizon Telescope in 2019, when it imaged the accretion disk around the supermassive black hole in Messier 87, revealing the ominous shadow of a black hole with a mass of 6.5 billion solar masses. The formation of these supermassive black holes is the subject of intense study and speculation. Unlike the vacuum cleaners of science fiction stories, real black holes attract matter by gravity rather than by active suction. This gravitational attraction becomes unusually strong at close distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds, containing as much matter as millions of stars. This direct collapse model suggests that such black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes born under the stressful conditions of the Big Bang served as seeds for subsequent growth. By studying these colossal formations, we gain insight into the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It's not just a dramatic cosmic event, it's a transformational process that changes the very fabric of the universe. At the center of these galactic collisions are the same supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent. It sets in motion vast amounts of ambient gas and dust, creating a turbulent environment ripe for extraordinary phenomena. Physicists have modeled these colossal mergers and found that as black holes spiral closer together, they can produce incredibly energetic jets of electromagnetic radiation. They fly out along the axis of rotation much more powerfully than those typically observed around isolated black holes. The cosmic show begins even before the black holes fully merge, giving astronomers a potential warning of these events. When these supermassive black holes finally collide, their jets combine into single high-energy bursts. These may be accompanied by less directional bursts, increasing the chances of detection. The merger process sets the surrounding plasma in motion, causing powerful jets that can theoretically be observed from billions of light years away. The detection of these cosmic events is not just exciting, It provides a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can either strengthen the current understanding of gravity or open up new physics, potentially leading to alternative theories. Future missions such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to pinpoint these mergers. LISA, a joint effort between NASA and the European Space Agency, will orbit the Sun and detect gravitational waves emitted by such mergers. Combining gravitational wave data with electromagnetic observations will allow precise localization and detailed study of these energetic events. Until advanced instruments become operational, astronomers rely on existing observatories to detect electromagnetic jets. They provide a dynamic view of galaxy evolution, demonstrating how such mergers can dramatically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A, which is 4.3 million times the mass of the Sun. In mid-spring of this year, the giant of our galaxy revealed new secrets, thanks to the advanced observations of the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial to understanding these fields because it shows how light waves are oriented and allows us to understand the properties of a gas and the mechanisms at work in powering the black hole. Interestingly, the magnetic fields around Sagittarius A are strikingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass of 6.5 billion times that of our Sun. This similarity suggests that strong, organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes the possibility that Sagittarius A may contain a hidden jet intriguing. In other black holes, these fields drive powerful streams of matter. Although Sagittarius A appears relatively quiet, consuming a minimum of matter, the similar structure of its magnetic field hints at the possibility of a weak jettison that has yet to be observed. This new image of a black hole at the center of the Milky Way tells us that there are strong, swirling, and ordered magnetic fields near the black hole, explains Sarah Issa Un, study co-leader and NASA Hubble Fellowship Program Einstein Fellow at the Center for Astrophysics at Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHT, an array of telescopes around the world, that made these groundbreaking observations possible. By combining data from multiple telescopes, the EHT forms an Earth-sized virtual telescope capable of capturing unprecedented detail of black holes. Although Sagittarius A is closer to Earth, it presents a unique challenge because of its smaller size. The material swirling around it moves quickly, making it difficult to get clear images. In contrast, in the larger M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data for comparing black holes at opposite ends of the mass spectrum. The observed similarity in the magnetic fields between Sagittarius A and Messier 87 suggests that the central black hole of our galaxy may possess a hidden jet. If such a jet exists, it would provide new insights into the behavior and evolution of black holes and the galaxies in which they reside. The observation of this jet would be a great discovery, linking Sagittarius A to the energetic processes that form galaxies. The discovery of such a jet will greatly expand our understanding of how black holes affect their surroundings. Jets can expel gas and dust, affecting star formation and the overall evolution of galaxies. By comparing different black holes, astronomers will be able to identify the universal principles that govern these mysterious objects. Studying our own supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. Relativistic jets can have a dramatic effect on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A striking example of the influence of black hole jets is the Teacup Galaxy, located at a distance of about 1.3 billion light-years from Earth. The Teacup Galaxy got its name because of its peculiar handle structure, which was formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a vivid example of how even low-powered jets can significantly affect the environment. Even in the case of radio-quiet galaxies, jets can redistribute and disrupt the surrounding gas, and this will have an impact on the galaxy's ability to form new stars. Recent observations with the Atacama Large Millimeter Array have shown that jets in the Teacup Galaxy, although relatively weak, move, heat, and accelerate the galaxy's gas. Even in the case of radio-molten galaxies, jets can redistribute and disrupt the surrounding gas, and this affects the galaxy's ability to form new stars, explains Cristina Raus Almeida, an astronomer at the Instituto de Astrofísica de Canarias. The effects of these jets do not always occur head-on. The study found that the most significant effects in the Teacup Galaxy occur perpendicular to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates the gas. These interactions can prevent star formation by preventing the gas from cooling and collapsing into new stars. While strong jets can heat the gas in galaxies to such an extent that they slow its growth, preventing the formation of new stars, weaker jets, such as in radio-quiet galaxies, also play an important role. These jets can still stir up the gas in a galaxy, causing it to move and redistribute. Such activity can lead to the formation of new structures within the galaxy and affect its long-term evolution. Understanding the influence of these jets allows astronomers to piece together the complex puzzle of galaxy formation. Supermassive black holes are an integral part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weak ones. Stay tuned to explore together the forces that shape our universe.
Imagine for a moment that you are looking up at the night sky. The moon hangs there, a familiar silver disk, a constant companion in the vast dark. It feels distant, timeless, and silent. But there is a quiet stirring happening, a gentle shift in our relationship with that ancient light. A new chapter is beginning, not with a shout, but with a deliberate and patient breath. We are going back to the moon. But this time, we are not just going for a visit. We are going to learn how to stay. This is the heart of a plan called Artemis. Named for the twin sister of Apollo in mythology, it carries forward that legacy of exploration, but with a new intention. The goal is no longer just to plant a flag and leave footprints. The goal is to build a foundation, a place of learning and living, a small, fragile outpost on another world. A moon base. The very idea sounds like science fiction, a dream from a storybook. Yet step by careful step, that dream is being woven into a blueprint for reality. It will not appear overnight. That is the first thing to understand. There will be no sudden city of lights on the lunar surface. Instead, think of it as a seed planted with immense care that will grow slowly over years. NASA has envisioned a plan unfolding in 3 gentle stages. The first stage is about learning to walk again. It involves setting up the initial facilities to support missions, perhaps once a year. Astronauts will return to the lunar soil. their stays brief, their tasks focused on understanding the immediate environment, testing the simplest shelters, and beginning the work of resource mapping. It will be a time of reacquaintance, of touching the dust of another world and learning its texture, its challenges, and its gifts. The second stage will see those visits become more regular, more frequent. With each journey, a little more infrastructure will be delivered. A power system here, a communications node there. The base will begin to take a faint shape, like a constellation slowly becoming visible as the night deepens. The final stage is the long-duration habitation. This is when the seed truly sprouts. Modules that can house astronauts for weeks, perhaps months, will be nestled into the lunar landscape. It will become a place not just for exploration, but for continuous research, a laboratory under an alien sky. But where on the moon will this new home be built? The chosen site is a place of profound significance and mystery, the lunar South Pole. Unlike the equatorial regions visited by the Apollo astronauts, the South Pole is a land of extreme contrasts. Some crater floors there are plunged in permanent deep shadow, untouched by sunlight for billions of years. Within that endless cold, scientists believe water ice lies frozen, preserved in the eternal darkness. Just nearby, there are also high points, peaks of almost perpetual light, where the sun barely sets. These peaks of eternal light could provide near-constant solar energy. So this chosen location offers two of the most precious resources imaginable: the potential for water and the certainty of abundant power. It is a place of balance between eternal shadow and endless light. To build a home in such a distant and harsh environment, everything must be thought of. Every breath, every watt of power, every bite of communication. The plans for this base are a tapestry of quiet technology. It will need power, and the vision combines two sources: the steady, reliable warmth of nuclear fission and the clean, silent flow of energy from solar panels basking in the long lunar day. There will be rovers, both crewed and uncrewed, acting as gentle mechanical explorers and helpers. Some will be for astronauts to ride across the dusty plains, while others will operate on their own, scouting, carrying supplies, or preparing sites. Imagine machines that can level the ground, moving regolith, the moon's soil, to create stable foundations. Even the way people will talk and navigate will be recreated. There are plans for a communications network, a simple, reliable system not unlike a mobile phone network, but spanning the silent valleys of the moon, a lunar GPS system, using constellations of small satellites, will help guide every rover and every astronaut, painting a digital map over the ancient, cratered terrain. This entire endeavor is a symphony of partnership. It is not one nation working alone in the dark. NASA envisions working hand in hand with commercial companies and international space agencies. Different modules, different rovers, different rockets, all coming together in a shared purpose. It is a reminder that the dream of a moon base is a human dream, one that can be woven from many threads. You might wonder, how will the astronauts even get there? The original plan involved a way station, a small space station called the Gateway that would orbit the moon. Think of it as a quiet porch before stepping down to the surface. Orion spacecraft from Earth would dock there, and astronauts would transfer to a separate lander for the final descent. But plans, like rivers, sometimes find a new course. The current vision has simplified this journey. Now, the Orion crew capsule, after its long voyage from Earth, will meet its lunar lander directly in orbit around the Moon. There will be no stop at the gateway. Instead, the astronauts will float from one vehicle to the other and begin their descent. It is a more direct path, a straight line to the destination. And the hardware that was being built for the gateway? Those modules and systems will not go to waste. They will be repurposed, finding a new life as part of the base itself on the lunar surface. Nothing is lost. Everything is transformed. The journey back to the lunar surface is already underway. It has been over 50 years since the last human footsteps faded from the Moon's dust during Apollo 17. The Artemis program is the pathway back. Artemis Thakun will be a profound and beautiful mission. A crew of 4 astronauts will fly their Orion capsule around the far side of the Moon, farther from Earth than any humans have ever traveled. They will not land, but they will see with their own eyes the planet Earth as a distant blue marble against the black, and the Moon's hidden face, its far side, rolling beneath them. It is a shakedown cruise, a test of every system, and a reawakening of the human spirit for deep space. Following that, the steps continue. There was a plan for Artemis III to be the landing mission, but an extra flight has been added to the sequence. This careful, deliberate pacing means the next lunar landings will most likely occur during the Artemis IV and Artemis V missions. This addition is not a delay, but rather an act of patience, ensuring every piece is ready, every system is safe. The aim remains to see astronauts walk on the lunar surface once more before the end of this decade. So, what will it be like for those first crews to build this base? Picture them arriving, not to a prepared home, but to a collection of cargo delivered by earlier uncrewed flights. Their first task will be to wake the base up. They will connect power cables, activate life support systems, and inflate or assemble the initial habitats. The air inside will be manufactured, a bubble of Earth's atmosphere held tenderly inside a thin shell. The light will be artificial, warm, and constant, holding back the absolute blackness outside. The silence will be profound, broken only by the hum of machines and the sound of their own breath. Their days will be filled with purposeful work. They might deploy the first solar arrays, watching as the panels unfold like metallic wings to drink in the sunlight. They will test the rovers, taking the first cautious drives away from their habitat, their headlights cutting through the deep, sharp shadows. They will begin experiments, perhaps tending to a small growth chamber to see how plants respond to lunar gravity, which is only 1/6 of what we feel on Earth. They will collect samples, not just of rock, but of the regolith itself, studying its chemistry, its abrasiveness, its potential to be used as a building material or processed for oxygen. Every action outside will require a spacesuit, a personal spacecraft they wear. Each journey onto the surface, called an extravehicular activity or a moonwalk, will be a meticulous ballet. They will step through an airlock, watch the pressure drop to nothing, and then open the outer door to a landscape of breathtaking stillness. The dust will puff up around their boots, falling back in slow, graceful arcs in the weak gravity. They will see the Earth, a beautiful fragile crescent or a full blue disk hanging in the black sky, a constant reminder of home. The challenges are immense, but they are met not with force, but with gentle ingenuity. The dust is not like sand on a beach. It is sharp, glassy, and clingy, a remnant of eons of meteorite impacts. It will get into everything. So systems must be designed to keep it out, to clean it off. The radiation from the sun and deep space is constant, unfiltered by a magnetic field or a thick atmosphere. The habitats will need shielding, perhaps using the regolith itself piled over the modules like a protective blanket. The temperature swings are extreme, from searing heat in the sunlight to bitter cold in the shadows. The technology must be robust, simple, and reliable. But within those challenges lie wonders. The science that can be done from a permanent lunar base is transformative. The Moon is a history book of the solar system, its surface largely unchanged for billions of years. By studying its rocks and its craters, we can read the story of our cosmic neighborhood, understanding the bombardment that shaped the early Earth and perhaps even delivered the ingredients for life. The far side of the Moon, forever turned away from our noisy planet, is the quietest place in the inner solar system for radio astronomy. There, telescopes could listen to the faint whispers of the early universe, hearing signals drowned out on Earth. And then there is the larger dream, the quiet reason behind all this effort. The Moon is a proving ground, a classroom for a future that stretches even farther. Mars hangs in the sky, a red point of light, a world of profound fascination. But a journey to Mars is long and demanding. The Moon is our nearby neighbor, only a few days away. By learning to live and work on the Moon, to use its resources, to build sustainable habitats, to operate far from the immediate help of Earth, we are learning the skills we will need to one day make the journey to Mars. The Moon base is a stepping stone, not a destination. It is where we will practice for the next great voyage. Think of the view from a future lunar base window. An astronaut finishes their work, and before they sleep, they look out. The landscape is bathed in the soft gray light of Earthshine, sunlight reflected from our own planet. It casts a gentle glow, revealing the rolling hills and craters in monochrome detail. The stars above are piercingly bright, undimmed by atmosphere, a dense powder of light across the velvet black. The Earth itself might be visible, a blue and white swirl of clouds and oceans hanging in the silence. In that moment, the base is not just a collection of modules and machines. It is a sanctuary of human presence in an immense and empty sea. It is a testament to curiosity, to care, and to the quiet, persistent courage it takes to make a home in the unknown. The Moon has watched over our world since before life began. It has guided travelers, inspired poets, and pulled at the tides. For a brief moment, half a century ago, we touched it. Now, we prepare to return, not as visitors, but as students. We go to listen to its ancient stories, to learn its secrets, and to test our own capacity for stewardship beyond our home planet. The Artemis Moon Base is more than a plan. It is a promise to take the next gentle step into the cosmos, to extend the circle of our presence, and to carry with us not just technology, but a sense of wonder, responsibility, and peace. So the next time you look up at that familiar, silent orb in the night sky, know that a new light is being kindled, slowly and deliberately. A light of human presence, a small, warm glow in the vast, cool dark, whispering that we are beginning to learn how to stay. And as that presence grows, so too will the rhythm of life at this quiet outpost. Imagine the cycles, not of days and nights as we know them, but of sunlit periods and darkness, each lasting for about 2 Earth weeks. The base will learn to breathe with this rhythm. During the long lunar day, activity may hum a little louder. Solar panels will be at their peak, generating power, charging batteries for the night ahead. Rovers will traverse greater distances, their journeys plotted across the sun-bleached ground. Astronauts might venture out for longer excursions, setting up experiments or scouting new locations in the steady, shadowless light. Then, as the sun dips below the jagged horizon, a different mode of being will settle over the base. The temperature will begin its rapid plunge. The solar panels will fall silent, and the steady, unwavering heat from the nuclear power system will become the heartbeat of the habitat. The brilliant, harsh landscape will soften into shades of deep gray and black under the starlight. From inside, the windows will become mirrors, reflecting the warm interior light, showing the crew their own faces against the backdrop of the absolute night. Work will turn inward, to maintenance, to study, to communication with Earth. There will be time for reading, for writing, for simply gazing out at the stellar panorama. It will be a time of quiet consolidation, of waiting for the sun's return, a rhythm as old as the moon itself. The base will evolve through these cycles. After the first crews have established the initial foothold, later missions will bring expansion. New modules will arrive, carried on uncrewed landers, each one a new room for this extraterrestrial home. Some may be dedicated laboratories, with delicate instruments for analyzing lunar material in real time. Others might be workshops, where tools and parts can be fabricated using 3D printers, perhaps even using processed regolith as a raw material. There could be a greenhouse module where the soft glow of growth lamps nurtures rows of leafy greens, providing not just nutrition, but a vital psychological connection to living, growing things. The scent of soil and plants would be a precious reminder of a world far away. The very architecture of the base will likely be a blend of the brought and the built. Initial habitats may be inflatable, soft shells that expand to create spacious interiors after landing, offering more room for living and working within the tight constraints of a rocket's payload fairing. But as capabilities grow, so might the use of local materials. Experiments in using lunar regolith to create bricks or to print structures layer by layer could transition from concept to reality. Imagine a slow-growing shell around a habitat, not brought from Earth, but sintered from the very dust underfoot, providing that crucial radiation shielding. The base would then truly begin to grow from the moon itself, a gentle integration rather than just an imposition. The crewed and uncrewed rovers will form a quiet community of machines. The larger, pressurized rovers will be like mobile homes, allowing astronauts to embark on expeditions that last for several days, traveling far from the main base to explore distant craters or geological formations. They would drive during the day, and when night falls, they would simply park, the rover's interior remaining a warm, safe haven. The astronauts inside would share a meal, look at the maps of their journey, and sleep to the gentle hum of life support as the stars wheel silently overhead. Smaller, uncrewed rovers will act as scouts and helpers. Some might be tasked with constantly traversing the terrain, creating highly detailed maps. Others could be stationed at remote instrument packages, performing maintenance or collecting samples. They will communicate with each other and the base through that lunar network, a whisper of data flowing across the silent surface. The human aspect of this endeavor is perhaps the most profound. The astronauts who will live and work there are not just explorers and engineers. They are caretakers of a tiny, isolated world. Their teamwork, their patience, and their resilience will be the most essential systems of all. They will develop new routines, new ways of living together in a confined and remote space. They will celebrate birthdays and milestones with packets of special food sent from Earth. They will share the wonder of their view with school children in classrooms across the globe. Their video calls a live link from the most distant classroom imaginable. They will experience the unique, poignant perspective of seeing their home planet as a whole, a beautiful and isolated sphere, which often brings a deep sense of connection known as the overview effect. From the moon, Earth is unmistakably a world without borders, a fragile oasis. The research conducted will touch on every aspect of science. Biologists will study how life, from microbes to plants, adapts to lunar gravity and radiation, knowledge critical for long-term space travel. Geologists will have a field laboratory on a world with a history different from Earth's, unlocking secrets of planetary formation. Physicists might conduct experiments in the pristine vacuum, or study the solar wind as it directly strikes the lunar surface. And as mentioned, the potential for astronomy is breathtaking. On the far side, shielded from the radio noise of Earth, astronomers could deploy simple radio telescopes to listen to the faint signals from the earliest epochs of the universe, hearing the echoes of creation itself in a silence found nowhere else. This steady, sustained presence also changes our relationship with the moon culturally and legally. It becomes a place of work, of study, of habitation. The Artemis Accords, a set of principles agreed upon by nations participating in this journey, outline how we will act responsibly, promoting peaceful cooperation, ensuring transparency, committing to the safe disposal of debris, and pledging to protect historic sites like the Apollo landing areas. It is a framework for becoming good neighbors even before the neighborhood exists. It acknowledges that this venture is for the benefit of all humanity. The path to Mars, so often spoken of, becomes more tangible through this lunar work. Every technology tested on the moon is a candidate for the Martian journey. The life support systems that recycle air and water with high efficiency, the habitats that protect against radiation and dust, the techniques for using local resources to make fuel or building supplies, all these are rehearsals. The moon offers a place to make mistakes and learn lessons only 3 days from help, rather than the months it would take to return from Mars. The psychological understanding of a small crew living in isolation for long periods, managing their health and their morale, will be invaluable. The moon base is the most realistic dress rehearsal for interplanetary travel we can possibly stage. And so, as the years pass, the base will mature. What began as a few interconnected modules may grow into a small campus. There might be separate areas for landing and cargo, keeping the dust from frequent arrivals away from the main living quarters. Paths worn by rover wheels will become familiar roads on the lunar surface. The infrastructure, the power grid, the communications towers, the navigation beacons will become more robust, more invisible, simply part of the environment. It will become, in its own stark and beautiful way, a place. For those of us watching from Earth, the presence of the base will become a gentle constant. We will follow the cycles of crews arriving and departing. We will see images not just of astronauts in spacesuits, but of daily life. A scientist examining a rock sample at a lab bench, a meal being shared around a small table, a hand tending to leaves in the greenhouse. The moon will transform in our collective imagination from a distant symbol into a place where people live and work. It will become familiar, The night sky will hold a new point of reference. On a clear night, when you look at the moon, you might gaze toward its south pole, knowing that there, nestled in the contrast of light and shadow, is a tiny pinprick of human warmth. You might imagine the soft glow of a window, a light left on in the cosmos. In that light, all the quiet efforts, the careful planning, the patient science, and the courageous journeys are distilled. It is a light of perseverance. The ultimate purpose of this endeavor stretches beyond even Mars. It is about cultivating a capability, a resilience. It is about learning to live sustainably, not just on Earth, but as a species that can gently extend its reach into the solar system. It is an exercise in long-term thinking, in international cooperation, in peaceful technological development. The moon base is a tool for learning how to be better stewards, both of our home planet and of any new environments we may one day gently inhabit. So, as we drift in thought through the quiet vastness, let the image of this nascent base rest in your mind. See it not as a loud conquest, but as a careful insertion of a quiet heartbeat onto a silent world. It is a testament to humanity's most enduring qualities, our curiosity, which compels us to ask what is over the next hill, our ingenuity. Imagine for a moment that you are floating. You are perfectly weightless, perfectly still, in the deepest, softest darkness you have ever known. There is no sound here, only a profound and gentle silence. And as your eyes adjust, you begin to see them. Not just one or two, but countless points of light, scattered like fine diamond dust across an endless velvet curtain. This is the view from home. This is our night sky, and from this quiet, familiar place, let us begin a journey. Not a journey of speed or noise, but one of slow, wondering thought. Let us drift together with a gentle curiosity and ask a simple, spacious question. What lies above our solar system, and what, in the grand scheme of things, could possibly lie below it? To start, we need to find our footing, or rather, our floating place. So picture our solar system, not as a diagram in a book, but as a quiet, slow-moving dance in the void. At the heart of it, of course, is our sun, a warm, nurturing sphere of light and energy, holding everything in its gentle gravitational embrace. Around it, the planets trace their patient, elliptical paths. Mercury, Venus, our own Earth with its blue and white swirl, Mars, the giant Jupiter, ringed Saturn, the ice giants Uranus and Neptune. They are all there, along with moons and asteroids and comets, all moving to the same timeless rhythm. This is our immediate neighborhood. This is the realm we are beginning to know. It feels vast to us, and it is. To cross it, even in our fastest spacecraft, takes years, decades. But tonight, let us expand our sense of scale. Let us drift upward and see what lies beyond the last known orbits of our own celestial family. As we rise, so quietly, above the plane where the planets spin, we leave behind the last whispers of the solar wind. We pass the distant icy realm of the Kuiper Belt, where Pluto and its companions make their slow circuits. The sun from here is just the brightest star among many. And then we cross a threshold, a boundary that is not a wall, but a subtle shift in the balance of forces. This is the edge of the sun's dominant influence, a place called the heliopause. Here, the particles streaming from our sun finally meet the thin ancient gas that fills the space between the stars. This is the beginning of interstellar space. It is not empty. It is filled with what astronomers call the local interstellar medium, a diffuse mist of hydrogen and helium, wispy and cold, with here and there a tiny grain of dust, smaller than a particle of smoke. This is what exists in the great above of our solar system, an ocean of near-nothingness, but an ocean nonetheless. And sailing through this ocean are the other stars. From this new vantage point, we can look back and see our solar system for what it truly is, a single star system, adrift in a much greater sea. And our sun is not alone. It has neighbors. The very closest is a faint red dwarf star called Proxima Centauri. It is part of a triple star system we see as the bright point of Alpha Centauri. That light, which takes a little over 4 years to travel to our eyes, is our next-door neighbor. But next door, in a cosmic sense, is almost beyond comprehension. That distance, over 4 light years, is so immense that if we shrank the sun to the size of a grapefruit here on Earth, Proxima Centauri would be another grapefruit, over 1,000 miles away. All that space between them, that is what exists above us, a staggering volume of quiet, dark space punctuated by the lonely lights of other suns. And as we let our gaze soften, we see that these stars are not scattered randomly. They form patterns and swirls and great associations. Our sun, along with Proxima Centauri and many others, is part of a loose cluster, a stellar stream, all moving together through the galaxy. We are, in a sense, part of a tribe of stars, born from the same cloud of gas and dust eons ago, now slowly drifting apart on their own long journeys. This is a comforting thought. Even as we voyage into the great above, we are still with family. We are part of a local flock, sailing through the interstellar medium. But the story does not end with the nearest stars. If we continue to drift outward with infinite patience, a grander shape begins to emerge from the darkness. Those thousands of stars we see from Earth, and the countless more we cannot, are gathered into a colossal spinning structure, a vast island of stars, gas, and dust, our galaxy, the Milky Way. From within, it looks like a pale river of light across our sky. But from our imagined position far above the solar system, we would see its magnificent architecture, a brilliant, bulging core of ancient stars surrounded by a great spiraling disk where newer stars like our sun are being born. And our solar system? We are out here, in one of the spiral arms, about halfway from the brilliant center to the quiet outer edge. We orbit that galactic core once every 230 million years, a stately, slow dance we are all part of. So, above our solar system, there is the interstellar medium, there are the nearby stars, and there is the entire breathtaking wheel of our galaxy, turning with a silence that is almost musical in its grandeur. And yet, the galaxy is not the end of things. The great above stretches further still. If we could pull our perspective back, we would see that our Milky Way is also not alone. It has its own family. We are part of a small cluster of galaxies, gravitationally bound to one another, called the local group. Here lives the great Andromeda Galaxy, a spiral even larger than our own, a smudge of light in our night sky that is actually 1 trillion stars. There is the Triangulum Galaxy and dozens of smaller dwarf galaxies, all dancing around one another in the immense blackness. This group, millions of light years across, is our immediate intergalactic neighborhood. And beyond the local group, more groups, more clusters. They gather into immense filaments and walls, the largest structures in the known universe, tracing a pattern like a cosmic web against the darkness. In the spaces between these great webs are the voids, vast, empty regions of space that can be hundreds of millions of light-years across, containing almost no galaxies at all. So, when we ask what is above our solar system, the answer unfolds like an endless, gentle revelation. Above us is an ocean of near-nothingness, dotted with islands of stars. Those islands gather into archipelagos of galaxies, and those archipelagos form continents of structure, all set in a sea of unimaginable peaceful nothing. It is a hierarchy of quiet belonging, from our living room on Earth all the way out to the cosmic web. It is all above us, in every direction we look. But now, let us turn our gentle curiosity to the other part of the question. What could possibly lie below our solar system? This is a trickier thought, because in space there is no true up or down. But if we think of below not as a direction toward our feet, but as a direction inward toward smaller and smaller scales, a whole new universe of wonder opens up. It is a universe not of vast emptiness, but of incredible complexity and ceaseless activity. It is the universe within. So let us journey downward from the familiar scale of our solar system. We begin with our own world, the Earth. Below the system is the planet itself, with its mountains and oceans, its forests and cities, and below that, the intricate web of life. Every leaf, every insect, every breath you take is part of the solar system, existing below the grand orbital mechanics. Your very body, made of stardust, is a part of this cosmic neighborhood. You are a citizen of the solar system, living on its third planet. That is the most intimate answer to what is below. It is us. It is all the life, the geology, the weather, the art, and love and quiet moments that happen in the shelter of our sun's light. But we can go further down. Let us shrink our perspective, down past the scale of cities, of trees, of humans, down to the world of the very small. Below the level of our eyesight, there is a bustling universe, the world of cells, of bacteria, of viruses. A single drop of water from our planet contains a miniature ecosystem, teeming with life forms that have their own rhythms and cycles. They live and die on a grain of sand, utterly unaware of the planets orbiting overhead. This biosphere, this thin, vibrant film on our planet's surface, is a fundamental part of what exists below the solar system. It is the part that is alive, the part that turns starlight into consciousness, and we go smaller still, to the molecular level, the air we breathe, the water we drink, the DNA that codes for life. All of it is a dance of molecules, atoms linking and unlinking in an endless, silent chemical ballet. And these atoms, every single one of them, have a story that leads directly back to the stars above. The carbon in your bones, the oxygen in your lungs, the iron in your blood, were all forged in the hearts of ancient stars that lived and died long before our sun was born. So, the below is not separate from the above. It is the same stuff, arranged in an infinitely delicate and precious way. The universe expressed in a living, breathing form. Deeper we go, to the atomic scale, a realm of incredible emptiness and frantic energy. A single atom is mostly empty space. If the nucleus of a hydrogen atom were the size of a marble, the electron whirling around it would be over a mile away. Almost all the solid matter we feel is, at its heart, empty space, held together by invisible forces. This is a profound thought. The ground beneath your feet, the chair you sit on, your own hand, all are vast, open lattices of tiny points of energy humming in the void. We are, all of us, made of space and light and force. And what lies below the atom? The subatomic particles, the protons and neutrons that form the nucleus, and the electrons that dance in their clouds. And within the protons and neutrons, we find the quarks, held together by gluons. This is the frontier of our understanding, the quantum realm. Here, the rules are strange and beautiful. Particles are also waves. Things can be in two places at once until we look at them. Empty space is not empty at all, but a seething, bubbling foam of potential where particles flicker in and out of existence. This quantum vacuum is the very foundation of all reality. It is the canvas upon which the universe is painted. So, below our solar system, below our planet, below our bodies, down at the very bedrock of existence, there is this humming, vibrant field of potential. The solar system, with all its planets and moons, is a pattern, a fluctuation in this fundamental energy field. It is a gentle ripple on a deep, quiet, and unimaginably powerful sea. So we have two journeys, one outward, into ever greater scales of space and majesty, and one inward, into ever smaller scales of complexity and mystery. And they meet in a beautiful circular thought. The vast cosmic web of galaxies and the frothing quantum foam are not opposites. They are two expressions of the same single universe. The forces that hold a galaxy together, gravity, are the same forces that were set in motion at the very beginning. The quantum rules that govern a single electron are the rules that allowed atoms to form, then stars, then planets, then us. Our solar system is the meeting point of these two infinities. It is the middle ground. It is not insignificant because it sits between the immensely large and the incredibly small. It is, in fact, the precious bridge between them. It is the place where the universe, through billions of years of patient work, arranged stardust into a form that could look back out at the stars and wonder about them. We are the universe becoming aware of itself, and we exist right here, in this solar system, on this planet. As we float here in our minds, between the infinite above and the infinite below, a deep sense of peace might settle over you. There is no need to feel small. Instead, feel connected. You are literally made from the debris of exploded stars. The calcium in your teeth, the potassium in your nerves, the phosphorus in your bones, all were cooked in stellar furnaces. You are a way for the cosmos to know itself, and you exist in a location that is both spectacularly ordinary and miraculously rare. An ordinary star in an ordinary galaxy, but on a planet that is just the right distance, with just the right chemistry, to spark and sustain the flame of awareness. Think of the night sky again. Every point of light you see is a sun, and many of those suns likely have planets of their own. Some of those planets may have their own oceans, their own mountains, their own quiet nights. And on some, perhaps, other beings are looking up at their sky, seeing our sun as just another faint star, and asking the same questions, wondering what lies above and below their own celestial home. This thought does not isolate us. It connects us across the light years. We are all, everywhere in the universe, children of the stars, living on islands in the great dark, pondering the mystery of our existence. So, as this journey of the mind comes to a gentle close, let us return to that feeling of floating, the gentle darkness, the silent, steady points of light. There is no rush. There is no endpoint to reach. The wonder is not in a destination, but in the journey itself, and in the quiet realization it brings. Above us, an expanse of majestic, peaceful architecture built from gravity and time. Below us, a world of intricate humming complexity built from quantum whispers and stellar legacy. And here we are, suspended perfectly between them, in the gentle light of our sun. You are not just in the universe is in you. And in this quiet moment, that truth can be a deep and soothing comfort. There is no separation. You belong to this cosmos, from the smallest quark in your cells to the most distant galaxy spinning in the void. It is all one, vast, interconnected whole. And for tonight, that is enough. That is more than enough. So let the sense of scale dissolve. Let the question soften into simple awe. And just be here, a conscious part of it all, breathing slowly under the same ancient stars that guided our ancestors and will guide generations to come. The universe is above you, below you, and within you. And it is in this moment perfectly still, perfectly peaceful, and full of a quiet, endless wonder. Rest now in that knowing. And as you rest in that knowing, let your imagination linger on that bridge, that middle ground which is our home. Think of the solar system not as a collection of separate objects, but as a single, flowing entity. The sun's light and wind flow outward, touching every planet, every comet, every speck of dust, in a vast, spherical bubble called the heliosphere. This is our star's true domain, its gentle influence creating a protective cocoon against the true interstellar medium. We live inside the sun's atmosphere in a sense. Every time you feel sunlight on your skin, you are feeling the outermost, most tender reach of a stellar giant, a touch that has traveled for 8 minutes across the void to warm you. That connection is immediate and physical. It is a daily reminder that we are not merely observers of this system, but participants, bathed in its constant, life-giving stream. Consider the paths traced through this space, the orbits that have continued with such faithfulness for billions of years. They are not just lines on a chart. They are a slow, celestial harmony. Jupiter, with its great gravity, shepherds asteroids and shapes the architecture of the inner system. Saturn's rings, composed of countless ice particles, each following its own perfect orbit, create a spectacle of silent, clockwork beauty. The solar system is in motion, but it is a motion of profound peace, of balance so delicate and yet so resilient that it has cradled life for eons. This is the rhythm that exists below the galaxy's grand spin, a softer, closer rhythm, the rhythm of a year, of a season, of a moon cycle. These are the pulses of our immediate cosmic home, rhythms written into the biology of every living thing on Earth. Your own body responds to these cycles in ways subtle and deep. You are tuned to the music of this middle realm. Now, let your mind drift back to that concept of below, to the quantum world, and see if you can feel the connection to this celestial scale. It is a connection not of size, but of pattern, of relationship. The atom, with its nucleus and orbiting electrons, is so often compared to a miniature solar system. While the physics are profoundly different, the echo of that pattern is a soothing one. It suggests a universe that finds certain forms beautiful, certain arrangements stable, from the unimaginably small to the breathtakingly large. It is a hint of a deeper unity. The force that holds the electron in a loose embrace around its nucleus is electromagnetism, and that same force, in a different guise, is the force that makes the sunlight warm, that drives the chemistry of life, that allows your nerves to carry thoughts. The threads weave through every layer of reality, binding them. Think of the very act of perception that allows this journey. The light from a distant star, traveling for centuries, finally enters the eye of a being on a small, rocky world. That light, a packet of energy, a quantum phenomenon, strikes a molecule in a retinal cell, causing a change that becomes an electrical signal, which becomes a pattern in the brain, which becomes an image, a feeling, a thought of wonder. The entire universe, from the quantum to the galactic, is involved in that single moment of awe. The above and the below collaborate to create the experience of being here now, conscious. You are the locus where these vast scales meet and are translated into meaning. There is no more intimate point in the cosmos. Perhaps now we can contemplate the spaces in between these scales, not just the vast interstellar voids, but the quieter spaces closer to home, the space between planets, which we often think of as empty. But it is not empty. It is filled with the solar wind, a breeze of particles streaming from the sun. It is threaded by magnetic fields, invisible lines of force that guide and protect. It is dusted with microscopic grains, the leftover stuff of planetary formation, drifting like snow in slow motion, and occasionally, graced by the passage of a comet, a visitor from the system's outer reaches, leaving a temporary glowing trail as it is warmed by the sun. This interplanetary space is an environment, subtle and gentle, through which the worlds move like great ships on a calm, invisible sea. And what of the spaces within our own world, the deep ocean trenches where sunlight never reaches, and yet life thrives by chemosynthesis, drawing energy from the Earth's own hot interior? The vast subterranean networks of rock and aquifer where water moves slowly through the dark over centuries. These are inner spaces that feel as alien and remote as any planet, yet they are integral parts of the below that supports the vibrant surface. They remind us that complexity and resilience exist in the dark and the quiet, not just in the light. Our planet has its own hidden depths, echoing the cosmic ones. As we float with these thoughts, we might also consider time as a dimension of this journey. What exists above and below can also be thought of as what came before and what will come after. Below, in the past, is the protoplanetary disk, the swirling cloud of gas and dust that coalesced into our sun and its planets. It is the long, slow cooling of the Earth, the first tentative molecules of life in a warm little pond. It is the age of dinosaurs, the rise of mammals, the dawn of human consciousness looking up at the same stars. Above, in the future, is the continued slow drift of the stars, the eventual merging of our Milky Way with the Andromeda Galaxy in a slow-motion dance that will reshape the night sky over billions of years. It is the sun, growing older, warmer, eventually becoming a red giant and then a quiet white dwarf. The solar, imagine for a moment that you are looking up at the night sky. you find that bright, steady point of light, not a star, but a planet. Jupiter. It has been a constant presence for all of human history, a wandering star to the ancients, a swirling marble of cloud to the first astronomers who pointed their telescopes its way. It feels permanent. It feels known. But out there, in the deep quiet of space, something is happening. Something subtle and strange and slowly unfolding. Jupiter is not quite behaving as we thought it would. It holds secrets beneath its famous bands, mysteries in its endless storms, and recent whispers from science suggest we are only just beginning to understand the true nature of this giant world. So let us drift toward it tonight, not with urgency, but with a soft and wondering curiosity. Let us explore what it might mean when we say that something weird is happening to Jupiter. To understand the strange, we must first appreciate the familiar. Jupiter is a world of magnificent scale. It is so large that all the other planets in our solar system could fit inside it with room to spare. It is not a solid world of rock and soil like our own, but a gas giant, a vast sphere of mostly hydrogen and helium with no surface to speak of, only layers of atmosphere growing denser and hotter until they blend into a strange metallic fluid deep within. Its most famous feature is the Great Red Spot, a storm wider than our entire planet that has raged for centuries, perhaps longer. From afar, through telescopes and the lenses of spacecraft, Jupiter presents a face of serene and beautiful turmoil. Swirling bands of cream, ochre, and tan stripe its face, flowing in opposite directions, driven by jet streams that race at hundreds of miles per hour. It is a dynamic world, a churning cauldron of weather, and for a long time we thought we understood its rhythms. We thought its immense distance from the sun, its own internal heat radiating from a slowly shrinking core, and its rapid rotation created a system that was, in its own violent way, predictable. But the closer we look, and the longer we watch, the more we see patterns that puzzle us. The giant is whispering, and we are slowly learning to listen. One of the most profound mysteries of Jupiter has always been what lies beneath those magnificent clouds. The cloud tops we see are just the outermost layer of an atmosphere thousands of miles deep. They are so thick, so dense, and so turbulent that they have acted as a perfect veil. No probe has ever penetrated far enough to tell us what is below. The Galileo spacecraft, when it ended its mission, was sent plunging into Jupiter's atmosphere, and it transmitted data for only about an hour before the immense pressure and heat crushed and vaporized it. It was like throwing a stone into an ocean and trying to understand the seafloor from the briefest splash. So, for centuries, we have been astronomers peering at the surface of a deep, deep sea, trying to guess the creatures and landscapes that dwell in its abyss. What is the true composition of Jupiter? How much water is hidden down there? How much oxygen? These are not just questions about one planet. They are clues to the very beginning of our entire solar system. Jupiter was likely the first planet to form, and its composition is a frozen recipe from the primordial cloud of gas and dust that gave birth to our sun and all the worlds that orbit it. To understand what Jupiter is made of is to understand our own origins. Recently, scientists have taken a new approach to this ancient puzzle. Instead of just observing the cloud tops, they have begun to build incredibly detailed digital simulations, combining the physics of fluid motion with the complex chemistry of thousands of reactions. It is like creating a Jupiter in a supercomputer, a virtual world where they can experiment and observe processes that are impossible to see directly. And this new model has revealed something quite significant. It suggests that Jupiter likely holds much more oxygen than we previously suspected. In fact, the estimate is that Jupiter contains about 1.5 times more oxygen than our Sun. This is a key piece of the puzzle. If Jupiter, the solar system's firstborn, has that much oxygen, it changes the story of how the building blocks of planets were distributed in that early cosmic cloud. It hints that the region where Jupiter formed was richer in certain icy materials than we thought. This oxygen is not in the form of the air we breathe, of course. Deep within Jupiter, under crushing pressures, it is bound with hydrogen to form water or mixed into other exotic compounds. This finding helps resolve a long-standing debate and sharpens the picture of our solar system's infancy. But it also highlights a deeper truth. The gases in Jupiter's immense atmosphere move and mix much more slowly than scientists once believed. The churning we see on the surface is just the very top of a profoundly sluggish, deep ocean of gas. Processes that might take years or decades in Earth's atmosphere could take centuries or millennia within Jupiter. It is a world operating on a timescale almost incomprehensible to us, a giant breathing with an unimaginably slow breath. This leads us to the other, more immediate strangeness. While the deep interior may be slow, the upper atmosphere where the clouds live is showing us patterns that defy our expectations in a different way. For 40 years now, we have been studying Jupiter's weather, not just with occasional spacecraft flybys, but with persistent observation from telescopes on Earth and in space. We have compiled a record, a 4-decade-long diary of Jupiter's temperatures and cloud movements. And this long view has revealed something odd. Jupiter experiences what look like hot and cold periods. Its upper atmosphere, in specific bands and at specific latitudes, seems to warm and cool in cycles. On Earth, such cycles are the heartbeat of our seasons, caused by the tilt of our axis as we orbit the Sun. But Jupiter's axis is only tilted by about 3 degrees. It spins almost perfectly upright. It does not have seasons in the way we understand them. There is no planetary reason for its equator to be significantly warmer or cooler than its poles in a cyclical pattern. And yet, the data shows these oscillations happening. It is as if the planet has its own internal rhythmic pulse of heat that has nothing to do with the distant Sun. The changes are not dramatic, not like a switch being flipped, but they are consistent and strange. They suggest that the engine of Jupiter's weather, the transfer of heat from its hot interior out into space, is far more complex and poorly understood than our textbooks suggested. The giant planet seems to be marching to the beat of its own, very slow and very mysterious drum. Think about what this means. Here is a world, the largest in our neighborhood, a fundamental anchor point in our solar system. We have mapped its storms, counted its moons, and sent robotic emissaries to orbit it. And yet, it is telling us that the basic forces that drive its climate are not what we modeled them to be. The planet is not acting quite like a planet should, according to our simpler models. It has its own logic, its own pace, its own hidden mechanisms that we are only beginning to sense. This is the quiet wonder of discovery. It is not about finding answers that fit neatly into boxes. It is about realizing the questions were not even big enough to begin with. Jupiter is reminding us of the humility of science. Every answer unveils a deeper, more intricate question. Consider the great red spot itself. We have watched it shrink and change color over the decades. We have seen smaller storms get swallowed by it, or sometimes crash against its swirling walls and break apart. It is a permanent yet changing feature, an island of fury in a fluid sky. But what fuels it? What keeps a storm alive for hundreds of years? The new understanding of slow atmospheric mixing and internal heat pulses might hold clues. Perhaps the spot is not just a surface weather pattern, but a chimney, a conduit for energy and material from the deep interior, which gives it a longevity no storm on Earth could ever hope to have. Its redness, likely caused by complex chemicals being dredged up from below and cooked by ultraviolet light, is a direct window into processes happening dozens of miles underneath the cloud tops we can see. It is a symbol of the hidden Jupiter, the world beneath the veil. And then there are the colors of Jupiter's bands, those beautiful tawny browns, tans, and whites. They are created by different chemical compounds, ammonia, ammonium hydrosulfide, and traces of water, existing at different altitudes and temperatures. The lighter bands are zones where gas is rising. The darker bands are belts where gas is sinking. This simple up and down motion, driven by Jupiter's fierce rotation, creates the striped pattern. But the new research suggests the chemistry governing these colors is immensely complex. Molecules are not just passively riding the winds. They are condensing into droplets, evaporating back into gas, and undergoing countless chemical reactions as they are transported from the hot, high-pressure depths to the cold, thin upper layers. The beautiful face of Jupiter is a constantly changing chemical painting, its palette determined by processes we are only now learning to simulate. What looks like a simple band of color is the end result of a planetary-scale alchemy, a slow distillation happening over epochs. So, when we say something weird is happening on Jupiter, we are not talking about a sudden, alarming change. We are not describing a cataclysm or an imminent transformation. The weirdness is in the subtlety. It is in the slow realization that this familiar giant, this king of planets, operates on principles more nuanced and mysterious than we gave it credit for. Its atmosphere mixes slowly. Its heat pulses in unexplained rhythms. Its composition tells a story of the solar system's birth that we are still deciphering. This is the calm, ongoing weirdness of a universe that is always more intricate than it appears. Jupiter is not breaking the rules. It is showing us that the rule book we wrote was only a first draft, a simplified sketch of a masterpiece. As you lie there, thinking about that distant point of light, you can picture it not as a static picture in a textbook, but as living, breathing entity, a world of unimaginable depth, where storms last for centuries and the air itself moves with the patience of geology, a world where the temperature fluctuates to a rhythm we cannot yet hear, driven by an inner fire and a logic all its own. The sense of wonder comes not from fear of the strange, but from a gentle appreciation of the vast unknown that resides even in our own celestial backyard. Jupiter has been there all along, holding its secrets close, revealing them slowly, one whispered datum at a time, across decades of patient observation. There is a profound peace in this realization. The universe is not a solved puzzle. It is a story that is still being told, and we are here, quiet and small, listening to one chapter of it. The weirdness on Jupiter is a gift. It is a reminder that curiosity is a gentle, endless journey. There will always be another layer to peel back, another question to ask, another mystery waiting in the soft glow of a distant world. So the next time you see Jupiter shining in the night sky, you can know that you are looking at more than a planet. You are looking at a question mark wrapped in clouds, a giant enigma spinning silently in the void, doing things we are just beginning to understand. And there is a deep, quiet comfort in that. The cosmos is alive with slow, majestic change, and our role is simply to watch, to learn, and to wonder. So, let your mind drift with that thought, as softly as a cloud drifting in Jupiter's upper atmosphere. There is no need for conclusions, only contemplation. The giant is there, as it always has been, doing something weird and wonderful, a testament to the infinite complexity of the universe we call home. And that is a thought peaceful enough to drift away on, into quiet and dreamless sleep, under the same sky that holds such gentle, endless mystery. And as we contemplate this slow-motion giant, we can begin to imagine the sensory experience of being there, not as a solid being, for there is no ground to stand on, but as a consciousness drifting through those layers. Imagine descending from the blackness of space, approaching those creamy, swirling cloud tops. The first thing you might sense is the silence, a profound and absolute quiet, for sound needs a medium to travel. And here, the medium is so thin and vast that a storm the size of a continent would make no audible roar to an outside observer. But within, if you could listen, the sound would be a deep basso profundo rumble, vibrations felt more than heard, the groan of a world under its own immense weight. You would pass through the high, wispy ammonia cirrus clouds, crystals sparkling in the faint sunlight that is only 1/25th as bright as it is on Earth. The light here is a perpetual soft twilight, tinged with gold and brown. As you drift deeper, the pressure builds, a gentle but insistent embrace that would quickly become crushing. The clouds thicken into bands, great rivers of atmosphere flowing in opposite directions. Here, in the zones and belts, you would be caught in jet streams moving at over 300 miles per hour, yet the scale is so grand that the motion might feel stately, inexorable, like being in the heart of a planetary tide. The colors here are not the vivid hues of enhanced spacecraft images, but more muted, subtle shades of cream, rust, and pale gray, with occasional flashes of deeper ochre where compounds well up from the abyss below. Deeper still, the sunlight fades completely. You are in the eternal night of Jupiter's middle atmosphere. Here, if there were eyes to see, they might perceive the ghostly glow of heat lightning, vast discharges of energy illuminating banks of clouds made not of water, but of ammonium hydrosulfide, giving off a faint sulphurous scent, if such a thing could be smelled. The temperature, curiously, might be quite comfortable here, even room temperature in certain layers, before plunging again and then beginning its final fierce climb into the inferno. This is a realm of perpetual chemical industry. Molecules split and recombine, forming intricate chains, condensing into droplets and vaporizing again, all in a slow, three-dimensional dance dictated by the slow circulation of the deep atmosphere. The new models tell us this dance is far more leisurely than we ever imagined. A parcel of gas carrying its unique signature of chemicals, might take centuries to complete a single loop from the deep interior to the cloud tops and back again. This is the sluggish heartbeat of Jupiter. And what of that deep interior? As we sink further, pressure turns the gaseous hydrogen into a fluid, and then, thousands of miles down, into a strange metallic liquid. This is not a place of familiar matter. It is an ocean of liquid hydrogen, electrically conductive, swirling around a core that is still a mystery. Perhaps a dense ball of rock and ice, perhaps a diffuse, diluted mixture of elements slowly dissolving into the surrounding metallic sea. The heat here is tremendous, left over from the planet's violent birth, and perhaps from the slow, gravitational squeezing of its own mass. This internal furnace is the ultimate engine for everything above. It is this heat, seeping outward with incredible slowness, that drives the convection, fuels the storms, and creates those mysterious thermal pulses in the upper atmosphere that we detect as warm and cool periods. The planet is radiating more than twice the energy it receives from the sun. It has its own source of warmth, its own inner fire, and the rhythm of that fire's release into the atmosphere is what we are only beginning to perceive as a weird, arrhythmic pulse. This brings us back to the question of why. Why do these thermal cycles exist without seasons? One contemplative possibility lies in the very slowness of the system. Jupiter is not just a ball of gas. It is a fluid planet through and through. The movements within its metallic hydrogen interior, the dynamo that generates its powerful magnetic field, the strongest in the solar system. These processes might have their own long-term cycles. Waves of energy, perhaps akin to the ocean oscillations on Earth, but on a planetary and century-long scale, could slowly propagate upward. They might be influenced by the complex gravitational tugs of Jupiter's many moons, especially the large Galilean ones. Io, Europa, Ganymede, and Callisto constantly stretch and squeeze Jupiter's interior through tidal forces, minutely affecting its fluid dynamics. Over decades, these subtle nudges could manifest as variations in how heat is distributed in the upper layers. It is a symphony of forces: internal heat, deep circulation, magnetic dynamics, and external tides, playing a piece so long that a human lifetime can only hear a few notes. What we call weird is simply our first faint hearing of this symphony. Consider the clouds themselves as characters in this slow drama. The white ammonia clouds are the highest, the cold ones. Below them, in a layer with more pressure and slightly warmer conditions, exist the ammonium hydrosulfide clouds, which give Jupiter its tawny browns and tans. Deeper still, where the pressure is dozens of times that of Earth's surface and the temperature climbs, there should be clouds of water vapor. This water layer is one of the great hidden realms. The new findings about abundant oxygen directly point to a wealth of water hidden in these depths, but accessing it, even with our most advanced simulations, is a challenge. This water cloud layer may be where some of the most significant weather occurs, a realm of droplets and storms entirely hidden from our view, yet its effects ripple upward to shape the patterns we see. A slow upwelling from this hidden ocean of vapor could, over many years, alter the chemistry and temperature of the upper cloud decks, contributing to the cyclical patterns we observe. There is also the fascinating interplay of chemistry and motion. On Earth, our weather is largely a physical phenomenon: temperature, pressure, wind. chemistry plays a secondary role. On Jupiter, they are intimately, fundamentally linked. The colors are chemistry. The storm longevity is chemistry. The very structure of the cloud layers is a chemical stratification. As gases rise from the hot depths, they cool. Different compounds condense out at specific temperatures and pressures, forming clouds at precise altitudes. But the new combined models show this is not a one-way street. These cloud droplets do not just sit there. They fall, they evaporate, they release latent heat, which in turn drives more circulation. They act as tracers, showing the pathways of the deep winds, and they shield the lower atmosphere from our view, creating the veil that has made Jupiter's composition so hard to pin down. The weirdness, then, is partly in realizing that Jupiter's atmosphere is not just a fluid system, but a chemical reactor of unimaginable scale. Its beauty is a direct visual output of its constant, slow, alchemical transformation. As we watch from our distant vantage point, with instruments growing ever more sensitive, we are essentially learning to read this giant's vital signs. The infrared glows that reveal temperature, the subtle changes in cloud color and reflectivity, the slight shifts in wind speed, measured by tracking cloud features over decades. These are Jupiter's pulse, its respiration, its slow blink. And the diagnosis so far is that it is a far more complex and interesting patient than we assumed. It defies simple categorization. It is not merely a failed star, nor is it simply a larger version of the other gas giants. It is its own unique class of world, the archetype of a gas giant. And it is teaching us that the archetype itself is richer and stranger than the definition we wrote for it. This has profound implications beyond Jupiter itself. We have now discovered thousands of planets orbiting other stars. A great many of them are gas giants, some larger than Jupiter, some orbiting perilously close to their suns. We call them hot Jupiters. For a long time, we used our solar system's Jupiter as the model for understanding all such worlds. But if our own Jupiter is more mysterious than we thought, how much more mysterious must those distant cousins be? Our Jupiter, with its complex, slow-moving atmosphere and internal heat cycles, provides a benchmark, but a benchmark that is now shimmering with complexity. It tells us that to understand exoplanets, we must first humble ourselves before the deep, slow mysteries of the one that resides in our own cosmic neighborhood. Every strange datum from Jupiter is a cautionary note, a reminder that the universe rarely simplifies itself for our convenience. So, as you let your mind wander across the gulf of space to that awfully banded sphere, try to feel the scale of time as well as space. Imagine a storm that began before the invention of the telescope, that has persisted through the entire modern age of humanity, and that shows only gradual, gentle change.